the vast emptiness of space, far beyond the familiar glow of our cities and the comforting light of nearby stars, there exists a place where all becomes still. Out here, far from cities, far from stars, there is only silence. And beyond that silence, darkness. We call it the border, not because we've seen it, but because we cannot. Tonight, we travel to where the cosmos fades, to its invisible edge, its quiet boundary, the silent border of the cosmos. Imagine yourself floating, weightless, in the deepest part of space. The Earth is now just a pale blue dot among countless others, fading into the distance behind you. As you drift further, the stars begin to thin out. Their light, once so abundant, now becomes precious and rare. Each photon that reaches your eyes has traveled for millions, perhaps billions of years, carrying ancient messages from worlds long gone. What lies beyond the faintest star? What exists in the space where light has not yet reached? These questions have haunted humanity since we first looked up at the night sky and wondered about our place in the universe. The border is not just a physical boundary, but a philosophical one. It marks the edge of our knowledge, the limit of what we can observe and understand. Tonight, we will journey together toward this silent edge. We will explore the known and ponder the unknown. We will travel through billions of light years, across galaxies and voids, until we reach the place where light itself surrenders to darkness. The cosmos is not static. It breathes, expands, and evolves. As it grows, so too does the silent border, always staying just beyond our reach. It is a horizon that recedes as we approach it, a boundary that exists not in space, but in our perception of space. As we begin our journey, take a moment to consider the scale of what we are about to explore. The Earth, our home, is but a speck in the vastness of space. Our solar system, a mere point of light in the Milky Way galaxy, and our galaxy, one among billions, perhaps trillions, scattered across the observable universe. Yet even this unimaginable expanse is finite. There comes a point where our instruments can see no further, where the light from distant galaxies has not yet had time to reach us, where the expansion of space itself outpaces the speed of light. This is the silent border we seek. The night sky above us seems eternal and unchanging, but it is merely a snapshot, a moment frozen in cosmic time. The stars we see tonight are not the stars as they are now, but as they were when their light began its journey to Earth. Some may have already died, their final moments yet to be witnessed by human eyes. Others are being born in stellar nurseries, their light still racing toward us through the void. In the darkness between stars, in the vast cosmic voids, silence reigns. Not the silence of absence, but the silence of distance, of space so vast that even light, the fastest messenger in the universe, takes billions of years to cross it. Listen closely to this silence. It speaks of beginnings and endings, of matter and energy, of time itself. The border we seek is not just a place where the universe ends, but where our understanding of it reaches its limit. It is a reminder of how small we are, and yet how remarkable it is that we can comprehend even a fraction of the cosmos. As we venture forth, remember that we travel not just through space, but through time as well. The further we look, the deeper into the past we see. The edge of the observable universe is also the beginning of all things, the echo of the Big Bang still reverberating through the cosmos. What will we find as we approach the silent border? Will we discover new physics, new understanding of the nature of reality itself? Or will we simply reach the limit of what can be known, a boundary beyond which lies only mystery? The cosmos does not reveal its secrets easily. It speaks in the language of light and gravity, of quantum mechanics and general relativity. It whispers in the cosmic microwave background, the faint afterglow of creation. It sings in the ripples of space-time caused by colliding black holes, and it falls silent at the edge of observation. As our eyes grow heavy and our minds drift towards sleep, let us carry this sense of wonder with us. Let us remember that above us, beyond the ceiling, beyond the atmosphere, beyond the solar system and the galaxy, lies a universe so vast and so ancient that we can scarcely comprehend it. And at its edge, the silent border waits. Not a wall or a barrier, but a threshold of understanding. A place where the known meets the unknown, where science meets mystery, where the finite touches the infinite. Tonight, we journey to that border, guided by the light of distant stars and the knowledge gathered by generations of astronomers and physicists. We travel not to conquer or claim, but to witness and wonder. To stand at the edge of all that is and gaze into the silence beyond. The silent border of the cosmos beckons. Let us answer its call. Yet all of these discoveries come from light, from electromagnetic radiation in various forms, from radio waves to gamma rays. Where light cannot reach us, knowledge fades. And at the cosmic horizon, light fails completely. The map ends where the light ends, but the silence begins much earlier. As we approach the edge of the observable universe, galaxies become fewer and fainter. They appear different too, younger and more chaotic, still in the process of formation. We see them not as they are now, but as they were billions of years ago, when the universe was in its infancy. These ancient galaxies tell us about cosmic evolution, about how the universe transformed from a nearly uniform gas into the complex structure we see today. They show us stars forming at rates hundreds of times higher than in the Milky Way, galaxies colliding more frequently, black holes growing more rapidly. But there is a limit to how far back we can see. The cosmic microwave background marks the edge of electromagnetic visibility, the point beyond which the universe was opaque. Before that time, 380,000 years after the Big Bang, photons could not travel freely but were constantly scattered by the hot, dense plasma that filled all of space. We can probe earlier times through other means. Neutrinos, nearly massless particles that rarely interact with matter, decoupled from the primordial plasma when the universe was just 1 second old. Gravitational waves could potentially carry information from the first fraction of a second after the Big Bang, but these messengers are far more difficult to detect than light, so our map of the cosmos remains incomplete. We see 93 billion light-years across, yet the universe may extend far beyond, perhaps infinitely. What lies beyond our cosmic horizon? More galaxies, certainly, more stars and planets, and perhaps more forms of life. But their details remain forever hidden, separated from us by the fundamental limits of light and time. The silence deepens with distance. The cosmos speaks to us through light, and where light fails, silence reigns. This is the beginning of the border. Not a physical edge, but a perceptual one, a limit to what can be known from where we stand. And yet, even this vast observable universe, stretching 46.5 billion light-years in all directions, represents only what we can see now. The true extent of the cosmos remains unknown. It may be finite or infinite, curved or flat, connected or disconnected. These questions lie at the frontier of cosmology, the science of the universe as a whole. What we know is that the visible universe is expanding and accelerating. Galaxies move away from each other, and the space between them grows. This expansion is not into some pre-existing void, but is the creation of space itself. There is no center to this expansion, no special reference point. From every galaxy in the cosmos, the rest of the universe appears to be moving away. As we contemplate the known universe, its vastness and complexity, its billions of galaxies and trillions of stars, we must also acknowledge what remains unknown. The map we have drawn is detailed but incomplete. It shows us the territory we can see, the realm of light and matter accessible to our instruments. But beyond this map lies more cosmos, silent and unseen, extending perhaps without end. The map ends where the light ends, but the silence begins much earlier. This picture becomes even more complex when we consider the accelerating expansion of the universe. Dark energy, the mysterious force driving this acceleration, causes the cosmic event horizon to shrink over time. Galaxies that are visible today will, in the distant future, accelerate beyond our event horizon, their light no longer able to reach future observers on Earth. The observable universe contracts even as the actual universe expands. In the far future, trillions of years from now, observers in the Milky Way, or whatever galaxy our descendants might inhabit, will see a very different night sky. Most galaxies will have accelerated beyond the event horizon, their light unable to counteract the expansion of space. The observable universe will consist primarily of the local group, a collection of galaxies gravitationally bound together, isolated in an otherwise empty and darkening cosmos. For these future observers, the evidence for the Big Bang, for a universe teeming with galaxies, for cosmic expansion itself, will have faded away. The cosmic microwave background will be redshifted to such long wavelengths as to be undetectable. Distant galaxies will be gone from view. If intelligence evolves at this late cosmic epoch, it might conclude that the universe consists only of a small collection of galaxies in an otherwise static, eternal void. This thought experiment reveals another aspect of the light-speed wall. It not only limits what we can see, but it also shapes what we can infer. Our cosmic theories, our understanding of the universe's origin and evolution, are based on observations possible only in our particular cosmic epoch. Future observers, or observers in sufficiently distant regions of space, might construct very different cosmologies based on the evidence available to them. The speed of light as a wall creates boundaries not just in space and time, but in knowledge itself. It defines the limits of the knowable universe, the border between what can be observed and what must remain forever hidden. This is the silent border we seek, not a physical edge, but a perceptual horizon, a limit imposed by the fundamental laws of physics. Yet this border is not static. It moves and shifts with time. The particle horizon expands as the universe ages, bringing previously unseen regions into view. The event horizon contracts as cosmic expansion accelerates, pushing once visible regions beyond our cosmic sight. The border breathes, expands, and contracts, a living boundary between the seen and the unseen. And what of the light that never reaches us? Photons emitted from stars beyond our event horizon continue their journey through space, traveling at their constant speed, crossing vast regions of the expanding cosmos. They carry information, images of worlds and stars, perhaps even civilizations, that we will never see. These are messages without recipients, signals traveling through an ever-emptying void. Perhaps, in some distant region of space far beyond our event horizon, observers look out at their own observable universe, study their own cosmic microwave background, and wonder about what lies beyond their own silent border. They too would be bounded by the speed of light, confined to their own observable bubble, unable to see or communicate with us. Our light would never reach them, just as theirs will never reach us. This symmetry of ignorance, this shared limitation, is a humbling reminder of our cosmic context. The universe does not revolve around Earth or humanity. We are not privileged observers, but participants in a vast cosmic drama, able to witness only a fraction of the full stage. The speed of light binds all observers equally, democratic in its constraints, yet there is a beauty in this limitation. The very law that creates our cosmic horizon also makes observation possible. Light, with its constant and finite speed, carries information across the void. Without it, we would be truly blind, unable to see beyond our immediate surroundings. The same physical law that creates the wall also builds the window. As we approach the edge of the observable universe, the light grows fainter, the signals weaker. Galaxies appear dimmer and redder, their light stretched by billions of years of cosmic expansion. The cosmic microwave background, the oldest light we can see, marks the edge of electromagnetic visibility, a wall of radiation beyond which traditional telescopes cannot peer. But even this is not the true border. The cosmic microwave background comes from when the universe was just 380,000 years old. Before that, the cosmos was opaque, too hot and dense for light to travel freely. Yet we know the universe existed during this earlier epoch. We can detect its after effects, study its imprint on the later universe, and even directly observe phenomena from slightly later times. The true silent border lies beyond, in regions so distant that their light, even traveling at its tremendous speed for the entire age of the universe, has not yet reached us. Out there, past the reach of light, is not darkness, it is absence. Not an absence of matter or energy, stars or galaxies, but an absence in our perception, a region that exists but cannot be observed. The speed of light is not just a velocity, it is a wall, a boundary, the defining parameter of our cosmic perception. It creates the silent border, the edge not of the universe itself, but of the knowable universe. Beyond this border, the cosmos continues, perhaps without end, filled with galaxies and stars, planets, and possibly life, all evolving and existing in regions forever hidden from our view. The wall stands, immutable and absolute, not built of matter or energy, but of physics itself, a constraint woven into the fabric of space-time. It is not to be breached or overcome, but to be understood and accepted. It defines the limits of our cosmic perception, the boundary of our observable bubble in the greater sea of existence. Out there, past the reach of light, is not darkness, it is absence. These questions have no easy answers. They push at the boundaries of science itself, forcing us to consider what constitutes evidence, what qualifies as knowledge, what separates science from speculation. They remind us that our cosmic understanding, impressive as it is, remains bounded by fundamental limits, constrained by our particular vantage point in space and time. Yet, despite these limitations, we continue to explore, to observe, to theorize. We push our instruments to their limits, squeezing every bit of information from the light that reaches Earth. We develop mathematical models that extend beyond what we can see, guided by the patterns we observe within our horizon. We test these models against new observations, refining our understanding of the cosmos step by step. In this quest, the silent border becomes not just a limit, but a guide, a reminder of the vastness beyond our vision, a challenge to our imagination and our intellect. It tells us that the universe is not just what we see, but what exists, whether visible to us or not. It reminds us that reality does not conform to our ability to perceive it, that the cosmos continues whether we can observe it or not. The edge we see may not be the edge that exists. Our cosmic horizon is a perceptual boundary, not a physical one. Beyond it, the universe continues, perhaps without end. Its galaxies and stars, its planets and possibilities, extending beyond our vision, but not beyond reality itself. The cosmos is not bounded by our ability to observe it. It exists independent of our perception, vast and ancient and ongoing, with or without our witness. The silent border marks not the edge of existence, but the limits of our knowledge, the boundary between the seen and the unseen, the known and the unknown. It is a horizon, not a wall, a threshold of perception rather than a barrier in space. The cosmos continues, but we cannot follow. History of the universe, from its earliest moments to the present day, to understand its composition and dynamics, to predict its future evolution. But this window of observability is temporary. In the far future, much of this evidence will have faded away, making it difficult or impossible for observers to discover the true nature of the cosmos. The horizons will have closed, not just limiting what can be seen, but restricting what can be known. This temporal aspect of cosmic horizons reminds us that our knowledge is constrained not just by where we are, but by when we are. Our particular moment in cosmic history, 13.8 billion years after the Big Bang, provides us with a unique perspective, a specific set of observable phenomena, a distinct window onto the nature of reality. Yet despite these constraints, we have learned an astonishing amount about the universe from the evidence available within our observable bubble. We know its age and composition, its history and structure, its fundamental forces and particles. We understand how stars form and die, how galaxies evolve, how the large-scale cosmic web emerged from tiny quantum fluctuations in the early universe. This knowledge, gleaned from studying the light that falls within our cosmic horizons, represents one of the great achievements of human inquiry. It places us in cosmic context, revealing our origins and our fate, connecting us to the larger universe of which we are a part. But the horizons remind us of how much remains unknown, how vast the cosmos may be beyond our bubble of visibility, how much of reality may lie forever beyond our reach. They humble us, constraining our knowledge, limiting our vision, challenging our understanding. They tell us that the universe is not just what we see, but what exists, whether visible to us or not. In this way, cosmic horizons serve as both limits and inspirations. They define the boundaries of our observable universe, the edges of our cosmic island in the potentially infinite sea of existence. But they also spur us to look deeper, to observe more precisely, to theorize more creatively about what lies beyond. They remind us that knowledge has horizons just as space does, that understanding, like light, can travel only so far in a given time. Particle horizon, event horizon, black hole horizon, early universe horizon. These boundaries shape our cosmic perception, define our observable bubble, constrain what we can know directly about the universe. They are not walls or barriers in the conventional sense, but thresholds of information flow, boundaries of causal connection, limits to communication across the cosmos. Beyond these horizons lie regions we cannot see, events we cannot witness, realities we cannot directly observe. They exist, they evolve, they may contain wonders beyond imagination, but they remain forever beyond our reach, separated from us by the fundamental laws of physics, by the speed of light, and the expansion of space. There are parts of the universe that will never speak to us again. The silence is both more profound and less complete than it first appears, a relative quiet rather than an absolute one. As we approach the edge of the observable universe, the silence deepens. Galaxies become fewer and fainter, their light stretched and dimmed by billions of years of cosmic expansion. The cosmic microwave background, faint as it is, dominates the electromagnetic landscape, a uniform glow in all directions marking the limit of visual observation. Beyond this lies not emptiness, but unseen territory, regions from which light has not yet reached us, or never will. The silence at the cosmic border is not from absence but from distance, not from emptiness but from separation, not from vacancy but from the finite speed of light and the expansion of space. It is a horizon of perception rather than a boundary in reality, a limit to our cosmic vision rather than an edge to existence itself. Even emptiness has weight. Even silence leaves a trace. The voids and spaces between galaxies, the regions of cosmic silence, influence the evolution of the universe through their gravitational effects, through their expansion, through their very existence. The cosmic web, the large-scale structure of filaments and clusters, forms in response to these vast empty regions, matter flowing away from voids toward denser surroundings, creating the complex tapestry we observe today. The voids themselves evolve, growing larger as matter flows outward, merging with neighboring voids to create ever more extensive empty regions. In the far future, as cosmic expansion accelerates, these voids will dominate the observable universe entirely, leaving only isolated islands of gravitationally bound matter in an otherwise empty cosmos. The silence will grow deeper, the emptiness more profound, as galaxies recede beyond our horizon, as stars burn out, as matter itself eventually decays. Yet even in this ultimate cosmic silence, fields and forces remain. Dark energy continues its relentless push, driving space apart with ever-increasing efficiency. Quantum fluctuations still permeate the vacuum, virtual particles popping in and out of existence. The background of neutrinos and highly redshifted photons, though incredibly diffuse, still permeates all of space. The silence is never complete, the emptiness never absolute, even in the most vacant regions of cosmic voids. This is the paradox of cosmic silence. The universe is mostly empty space, mostly void, mostly quiet by conventional standards. Yet this emptiness itself has structure. This silence its own form of eloquence. This vacancy its own fullness of a different kind. The quiet places of the cosmos are not nothing but something else, a different mode of cosmic existence, a complement to the more obvious structures of stars and galaxies. As we journey through these great silent places toward the edge of the observable universe, we must recalibrate our cosmic perception. The voids are not just absence but presence, not just background but foreground, not just emptiness, but structure of a different kind. They are the canvas upon which the luminous universe paints its patterns, the silence against which the cosmic symphony plays its notes. Even emptiness has weight. Even silence leaves a trace. Our journey begins with what we know, the map we have drawn of the visible cosmos. For thousands of years, humans have looked up at the night sky, charting stars and planets, searching for patterns in the celestial dance above. But it is only in the last century that we have truly begun to understand the scale and nature of our universe. The cosmos as we know it is composed of billions of galaxies, each containing billions of stars. Our own home, the Milky Way, is a spiral galaxy spanning roughly 100,000 light-years from edge to edge. A light-year, the distance light travels in one Earth year, equals about 9.5 trillion kilometers. Even at the incredible speed of light, 300,000 kilometers per second, it would take 100,000 years to cross our galaxy alone. And our galaxy is but one among many. The nearest large galaxy to us, Andromeda, lies 2.5 million light-years away. When you look at Andromeda in the night sky, you are seeing light that left its stars when our human ancestors were just beginning to use stone tools. This is the first lesson of cosmic distance. We never see the universe as it is, only as it was. Beyond our local group of galaxies lies the Virgo supercluster, a collection of galaxy clusters spanning more than 110 million light-years. And beyond that, countless other superclusters form the Great Cosmic Web, filaments of galaxies stretching across the void, separated by enormous bubbles of nearly empty space. The largest known structure in our universe is the Hercules Corona Borealis Great Wall, a supercluster complex spanning 10 billion light-years. Its vastness challenges our understanding of how the universe formed, suggesting patterns on scales we had not anticipated. Yet even this immense structure occupies only a fraction of what we can observe. Our instruments have peered deeper still. The Hubble Space Telescope, the James Webb Space Telescope, and other great observatories have captured light from galaxies so distant that we see them as they were less than a billion years after the Big Bang. These ancient galaxies appear different from those nearby, smaller and more chaotic, providing a window into the universe's youth. Between galaxies lies the intergalactic medium, vast regions filled with hydrogen and helium gas, so diffuse that it would be considered a perfect vacuum by earthly standards. Yet even this near emptiness contains more matter than all the stars combined. The universe is mostly void, with islands of light scattered like dust across an immeasurable ocean. But what we see is only a fraction of what exists. Dark matter, invisible to our telescopes yet detectable through its gravitational effects, makes up roughly 27% of the universe. Normal matter, the stuff of stars and planets and people, constitutes less than 5%. The remaining 68% is dark energy, a mysterious force driving the acceleration of cosmic expansion. The cosmic microwave background, faint radiation permeating all of space, offers our earliest view of the universe, a snapshot from when it was just 380,000 years old. Before that time, the universe was opaque, too hot and dense for light to travel freely. This radiation has been stretched by cosmic expansion, cooling from thousands of degrees to just 2.7 Kelvin above absolute zero. We have mapped the distribution of galaxies across billions of light-years, charted the cosmic microwave background, and detected gravitational waves from colliding black holes. Our knowledge extends across 93 billion light-years. The diameter, of the observable universe. It is a sphere centered on Earth, or more precisely, centered on whoever is doing the observing. For each observer in the cosmos has their own unique observable universe. Yet, as vast as this sphere is, it has a boundary, not a physical edge, but a limit to what we can see. Beyond this cosmic horizon lies more universe, perhaps much more, but it remains forever hidden from our view. The further we look into space, the more we notice something curious. Distant galaxies are moving away from us, and the further they are, the faster they recede. This is not because we occupy a special place, but because space itself is expanding, carrying galaxies along like raisins in rising bread dough. Edwin Hubble first observed this phenomenon in the 1920s, noting that the light from distant galaxies was shifted toward the red end of the spectrum, indicating they were moving away. This redshift increases with distance, a pattern now known as Hubble's law. The current rate of expansion, the Hubble constant, is approximately 70 kilometers per second per megaparsec, meaning that a galaxy 1 megaparsec away, about 3.3 million light-years, recedes at 70 kilometers per second. But as we look deeper into space, we find galaxies moving away much faster. Those at the edge of our observable universe recede at nearly the speed of light. And galaxies beyond that move away faster than light itself, not violating Einstein's theories because it is space itself that expands, carrying the galaxies with it. This expansion shapes the border of our cosmic vision. There comes a point where galaxies recede so quickly that their light can never reach us, no matter how long we wait. This is the cosmic event horizon, a boundary beyond which events are forever hidden from our view. The map of our cosmos is still being drawn. New telescopes and instruments probe ever deeper, revealing galaxies and structures previously unseen. The James Webb Space Telescope, with its infrared vision, peers through cosmic dust to witness star formation and galaxy evolution in unprecedented detail. Radio telescopes, like the Square Kilometre Array, scan the heavens for faint signals from the early universe. Gravitational wave detectors listen for ripples in space-time caused by violent cosmic events. Yet despite these technological marvels, there is a fundamental limit to what we can observe. The universe has been expanding for 13.8 billion years. But because this expansion has been accelerating, the most distant light reaching us now comes from objects that are currently about 46 billion light-years away. This is the radius of our observable universe, the furthest distance we can see in any direction. But this is not the end of all things. It is merely the end of our sight. The universe continues beyond, silent and unseen. As we venture deeper into space, another pattern emerges. The cosmos is not uniformly filled with matter. Instead, galaxies cluster together, forming a cosmic web of filaments surrounding vast, nearly empty voids. These voids can span hundreds of millions of light-years, regions so empty that if Earth were in their center, we would not know other galaxies existed until the 1920s, when our telescopes became powerful enough to see beyond our local group. The largest known void, the Boots void, spans 330 million light-years. If placed at its center, our most powerful telescopes would detect only a handful of galaxies in what appears to us as a sky filled with thousands. Such voids are not truly empty, but their matter density is less than 1/10 the cosmic average. These great cosmic voids challenge our understanding of structure formation. Why did matter cluster as it did? How did these vast empty regions form? The answers lie in quantum fluctuations in the early universe, tiny variations in density that, over billions of years, grew into the cosmic web we observe today. The silence grows deeper as we venture into these voids. Few stars shine there, few planets form. They are the quiet places of the cosmos, where the universe's voice fades to a whisper. Yet even in this near emptiness, light still travels, connecting one side of the void to the other, maintaining the cosmic conversation across millions of light years. But beyond the observable universe, even this connection is lost. No light crosses the boundary. No information flows from there to here. It is not just distant, It is disconnected, a region causally separated from our own. As our telescopes have improved, we have discovered not just the extent of the cosmos, but its history. We can trace the formation of the first stars, massive giants that lived fast and died young, seeding the universe with heavy elements. We can watch galaxies collide and merge, growing from small, irregular collections of stars into the majestic spirals and ellipticals that fill the universe today. We have detected planets around other stars, thousands of them, ranging from gas giants larger than Jupiter to rocky worlds similar to Earth. Some orbit in their star's habitable zone, where temperatures might allow liquid water and, potentially, life. The cosmos is not just vast in space, but rich in possibility. Light. It streams across the cosmos, carrying images of distant worlds, ancient galaxies, and the afterglow of creation itself. We depend on this messenger to reveal the universe to us. Yet light, for all its speed and reach, ultimately fails us. It becomes our barrier, our wall, the very thing that defines the silent border we seek. Light travels fast, almost incomprehensibly so. 300,000 kilometers each second, fast enough to circle our Earth 7.5 times in the span of a single heartbeat. In our everyday experience, light seems instantaneous. We flip a switch, and darkness vanishes without delay. We look up at the moon, seeing it as it exists in that moment, the light taking just over 1 second to reach our eyes. But the cosmos operates on scales that dwarf our human experience. When we gaze at the Sunday, we see it not as it is, but as it was 8 minutes ago. The light from our nearest stellar neighbor, Proxima Centauri, takes 4.2 years to reach us. The beautiful Andromeda galaxy, visible to the naked eye on clear, dark nights, appears to us as it existed 2.5 million years in the past, when our ancestors were just beginning to fashion stone tools on the African savanna. This delay grows with distance. The light from the Virgo cluster of galaxies, the nearest large galaxy cluster to our Milky Way, has traveled for 50 million years before entering our telescopes. The most distant galaxies visible to instruments like the James Webb Space Telescope emitted their light more than 13 billion years ago, when the universe was in its infancy. We see these ancient galaxies not as they are today, but as they were when the universe was less than 5% of its current age. This is the first paradox of cosmic observation. The further we look in space, the further we look back in time. Our telescopes are not just distance sensors, but time machines, revealing snapshots of cosmic history across billions of years. The universe we observe is a museum of the past, a collection of light that has been traveling for eons, only now reaching our eyes. But there is a limit to this cosmic time machine, a boundary beyond which we cannot see. This is the particle horizon, the maximum distance from which light could have reached us since the beginning of the universe. Given the age of the universe, approximately 13.8 billion years, one might expect this horizon to be 13.8 billion light-years away. But cosmic expansion complicates matters. As light travels toward us from distant galaxies, the space it traverses expands. This stretches the light waves, shifting them toward the red end of the spectrum, a phenomenon we call redshift. It also means that objects whose light reaches us from the early universe are now much further away than they were when they emitted that light. Their current distance, accounting for billions of years of cosmic expansion, is about 46.5 billion light-years. This is our current limit, the radius of our observable universe. It is not a physical wall, but a perceptual one, a boundary beyond which events cannot affect us, because their light has not had time to reach us since the beginning of the universe. Beyond this boundary lies more universe, perhaps much more, but it remains forever invisible to us. The speed of light is not just fast, it is absolute. Nothing with mass can travel at or beyond this cosmic speed limit. Even massless particles like photons cannot exceed it. This is a fundamental constraint of our universe, a central principle of Einstein's theory of relativity. The speed of light in vacuum is the same for all observers, regardless of their relative motion. a constant of nature, written into the fabric of space-time itself. This cosmic speed limit creates the silent border. The universe is approximately 13.8 billion years old, so we cannot see beyond a certain distance because light from there has not yet had time to reach us. It is still on its way, traveling at its immutable speed, crossing the vast gulfs of intergalactic space. Imagine a star that formed 12 billion light-years away from our current position. If it formed more than 1.8 billion years ago, its light has already reached us. We can see it as it was in the distant past. But if it formed just 1 billion years ago, its light is still en route, having covered only 1 billion light-years of its journey. We will have to wait another 11 billion years for that light to reach Earth. Future astronomers might observe it, but we cannot. And this is assuming the star remains within our cosmic horizon. But the expansion of space itself complicates matters further. As space expands, galaxies move away from each other, and the further they are, the faster they recede. This is not because they are moving through space at ever-increasing speeds, but because more space is being created between them over time. For galaxies beyond a certain distance, roughly 16 billion light-years in the current era, this expansion causes them to recede faster than the speed of light. Not because they break Einstein's cosmic speed limit, but because space itself is not bound by this limit. Space can expand at any rate, carrying galaxies along with it. This creates the cosmic event horizon, a boundary beyond which events will never be visible to us, no matter how long we wait. Light emitted from beyond this horizon will never reach us, because the space between expands faster than the light can travel across it. It is like running on a treadmill that speeds up faster than you can run, the destination always receding. Victory impossible. The silent border of the cosmos is defined by these twin horizons, the particle horizon that limits what we can see now, and the event horizon that limits what we will ever see. Between them lies a shell of space from which light is still en route to Earth. Photons that were emitted after the Big Bang, but have not yet completed their journey. Given enough time, light from this region will eventually reach us, revealing galaxies and stars currently hidden from view. But for regions beyond the event horizon, silence is permanent. No signal will ever cross that boundary. No light will ever breach that wall. It is not just unseen, but unseeable, a region causally disconnected from our own. The wall created by light's speed has another dimension, one equally profound. Not only does it limit what we can see, but it also constrains what we can know. Information in our universe cannot travel faster than light. This means that events beyond our particle horizon cannot have affected us in any way, cannot have shaped our past or influenced our present. They exist, but from our perspective, they might as well not. Similarly, events beyond our event horizon cannot affect our future. No matter what happens there, no matter what wonders might unfold or catastrophes occur, they will remain forever unknown to any observer in our region of space. It is as if these regions exist in separate universes, connected in principle by the shared origin of the Big Bang, but now evolving independently, each blind to the other's fate. This wall of light speed creates a fundamental limit to knowledge. There are parts of the universe that we not only do not know, but cannot know, not due to practical limitations of technology or resources, but due to the fundamental laws of physics. Even a civilization billions of years more advanced than ours, with technology we can scarcely imagine, would face these same constraints. The speed of light is democratic in its restrictions, binding the most primitive and the most advanced equally. The implications of this limitation are profound. The observable universe, vast as it is with its billions of galaxies and trillions of stars, may be but a tiny fraction of what exists. The true extent of the cosmos may be far greater, perhaps even infinite. Yet we are confined to our observable bubble, unable to directly study or experience what lies beyond. Moreover, if space is sufficiently large, there may be regions so distant that they have evolved completely independently from our own. The initial conditions set by the Big Bang would be the same, but quantum fluctuations would ensure that their precise development differs. Such regions might contain different distributions of galaxies, different evolutionary pathways, perhaps even different fundamental constants of physics. They would be, in effect, other universes embedded within the greater cosmos, separated not by physical barriers, but by the sheer vastness of space and the limiting speed of light. The universe is not static, it breathes, it grows. From the moment of its birth in the Big Bang, some 13.8 billion years ago, space itself has been stretching, carrying galaxies along in its cosmic flow. This expansion shapes everything we observe, from the redshift of distant galaxies to the very limits of what we can see. It creates the silent border, not by building a wall, but by stretching space faster than light can cross it. To understand this expansion, we must first abandon our intuitive notions of how objects move through space. In our everyday experience, things move against a fixed background. A car travels along a road, a bird flies through the air, even planets orbit their stars, within the seemingly stable framework of space. But cosmic expansion is different. It is not galaxies moving through space, but space itself, stretching between them. Imagine a loaf of bread rising in the oven. The raisins embedded in the dough do not move of their own accord, yet they grow more distant from each other as the bread expands. Similarly, galaxies do not rush away from each other through static space. Rather, the fabric of space-time stretches, increasing the distance between them without requiring them to move in the conventional sense. This concept first emerged from Einstein's general theory of relativity, which describes gravity not as a force, but as the curvature of spacetime caused by mass and energy. When Einstein applied his equations to the universe as a whole, he found something troubling. The mathematics suggested that the cosmos could not be static. It must either expand or contract. At the time, in the early 20th century, the prevailing view was that the universe existed in a steady state, eternal and unchanging. Einstein himself was so troubled by his finding that he added a term to his equations, the cosmological constant, to counteract gravity and maintain a static universe. He later called this his greatest blunder, not because the cosmological constant was necessarily wrong, but because he had modified his equations to match preconceived notions rather than following where the mathematics led. The observational evidence for cosmic expansion came in the 1920s through the work of Edwin Hubble. Using the 100-inch telescope at Mount Wilson Observatory, Hubble measured the distances to numerous galaxies and compared them with earlier observations of their spectra. He found that distant galaxies showed a redshift, meaning the wavelengths of light from these galaxies were stretched, shifted toward the red end of the spectrum. Moreover, Hubble discovered a pattern. The further a galaxy was from Earth, the greater its redshift. This relationship, now known as Hubble's law, provided the first empirical evidence that the universe is expanding. Galaxies are not moving away from us because we occupy a special place, but because space itself is stretching, carrying them along in its expansion. The rate of this expansion, the Hubble constant, tells us how quickly space stretches with distance. Current measurements place it at approximately 70 kilometers per second per megaparsec. This means that for every megaparsec, about 3.26 million light-years, a galaxy recedes an additional 70 kilometers per second due to cosmic expansion. Nearby galaxies, bound by gravity into the local group with our Milky Way, do not participate in this expansion. Their gravitational attraction overcomes the stretching of space. But beyond our local cosmic neighborhood, the effect becomes increasingly apparent. A galaxy 10 megaparsecs away recedes at 700 kilometers per second. One at 100 megaparsecs withdraws at 7,000 kilometers per second. As we look deeper into space, the recession velocities increase. Galaxies at the edge of our observable universe move away at speeds approaching that of light itself. And galaxies beyond a certain distance, roughly 16 billion light-years in the current era, recede faster than light. This seems to violate Einstein's cosmic speed limit, the principle that nothing can travel faster than light. But there is no contradiction. The galaxies themselves do not move through space faster than light. They remain relatively stationary within their local regions of space. It is space itself that expands, and this expansion is not constrained by the speed of light. Space can stretch at any rate, carrying galaxies along with it at apparent speeds far exceeding light's velocity. This superluminal recession has profound implications for our cosmic horizon. Light from galaxies currently beyond this boundary, about 16 billion light-years, will never reach us, no matter how long we wait. As these photons travel toward Earth, the space between expands faster than they can cross it. It is like swimming against a current that flows faster than you can swim. No matter how long or hard you stroke, you never make progress. In fact, you drift further from your goal with each passing moment. This is the cosmic event horizon, a boundary beyond which events are forever hidden from our view. Not because light from these regions has not had time to reach us yet, but because it never will. The expansion of space ensures that these regions remain permanently beyond our cosmic sight, their light eternally chasing a target that recedes faster than it can pursue. The universe has not always expanded at the same rate. In its earliest moments, during a period called inflation, it expanded at an exponential pace, doubling in size every tiny fraction of a second. This inflationary epoch, which lasted from about 10 to the negative 36 seconds to 10 to the negative 32 seconds after the Big Bang, stretched the universe by a factor of at least 10 to the 26, setting the stage for all that followed. After inflation, the universe continued to expand, but at a decelerating rate. The mutual gravitational attraction of all matter in the cosmos worked against expansion, slowing it down like friction resisting motion. For billions of years, this deceleration continued, and cosmologists expected that the expansion would either stop entirely in the far future, leading to a big crunch as the universe collapsed back on itself, or would continue forever at an ever-diminishing rate, approaching but never quite reaching zero. But in 1998, two independent teams of astronomers made a shocking discovery. By studying distant supernovae, exploding stars whose intrinsic brightness is well understood, they found that these cosmic beacons were dimmer than expected. This meant they were further away than their redshifts suggested they should be, given the then understood rate of cosmic expansion. The only explanation was that the expansion of the universe had not been slowing down as expected. Instead, it had been accelerating for the past 5 billion years. Something was pushing space apart, overwhelming the gravitational attraction that should have been slowing it down. This mysterious repulsive force, which acts like anti-gravity on cosmic scales, was named dark energy. It now appears to constitute about 68% of the energy content of the universe, far outweighing visible matter, which makes up less than 5%. The nature of dark energy remains one of the greatest unsolved mysteries in physics. It might be a property of space itself, a form of energy inherent in the vacuum, corresponding to Einstein's cosmological constant, or it could be something more exotic, a dynamic field that changes over time. Whatever its nature, dark energy has profound implications for the fate of the universe and for the silent border we seek. As dark energy pushes space apart with ever-increasing efficiency, the cosmic event horizon contracts. Galaxies that are visible today will, in the distant future, accelerate beyond our cosmic sight. Their light, once able to reach us, will find itself fighting against an increasingly rapid expansion of space, a battle it must eventually lose. In this way, the expanding universe does not just create a border, it makes that border dynamic, a boundary that shifts and breathes with cosmic time. The observable universe of the distant future will be smaller than it is today, not because the cosmos itself contracts, but because less of it remains visible to any observer. This expansion affects not just what we can see, but how we see it. As light travels across the expanding universe, its wavelength stretches along with space. This redshift alters the appearance of distant objects. Galaxies that emitted light in the visible spectrum may appear to us only in infrared, their light waves stretched beyond what our eyes can detect. The most distant objects, whose light has traveled for more than 13 billion years, are redshifted by a factor of more than 10, pushing even their ultraviolet emissions into the infrared. This redshift provides a window into the past. By measuring how much a galaxy's light has been stretched, astronomers can determine how much the universe has expanded since that light was emitted, revealing the galaxy's age and distance. The greater the redshift, the further back in time we see. But redshift also creates challenges. As objects approach the cosmic horizon, their light becomes so stretched that it grows incredibly faint and shifted to wavelengths that are difficult to detect. The cosmic microwave background radiation, the afterglow of the Big Bang, has been redshifted by a factor of 1,100, transforming what was once a brilliant glow at thousands of degrees to faint microwaves at just 2.7 Kelvin, above absolute zero. The expanding universe also shapes the overall geometry of space. Depending on the density of matter and energy, space could be curved like the surface of a sphere, flat like a sheet of paper, or curved like a saddle. Current observations strongly suggest that our universe is flat, or very nearly so, poised at the boundary between open and closed geometries. This flatness is thought to be a consequence of inflation, which stretched any initial curvature until it became imperceptible, just as the surface of a balloon appears flatter as it expands. This geometry affects the trajectories of light rays and the apparent positions of distant objects. In a closed universe, parallel light rays eventually converge, making objects appear larger than they actually are. In an open universe, they diverge, shrinking the apparent size of distant sources. In a flat universe, light travels in straight lines, preserving the true angular size of objects, adjusted only for distance. The expansion of the universe also affects its thermal history. As space expands, it cools. The early universe was incredibly hot, filled with a plasma of elementary particles too energetic to form stable atoms. As expansion proceeded, this plasma cooled, eventually allowing electrons to combine with nuclei to form the first atoms, primarily hydrogen and helium. This moment, about 380,000 years after the Big Bang, marks the transition from an opaque to a transparent universe, the time when light could first travel freely through space. This cooling continues today. The cosmic microwave background, once a searing radiation field, now hovers just above absolute zero. In the far future, as expansion accelerates, this temperature will drop even further, approaching but never quite reaching absolute zero. The universe grows colder with each passing eon, a direct consequence of its relentless expansion. This expansion creates a one-way flow of cosmic history. The universe began hot and dense, expanded and cooled, formed stars and galaxies, and now enters a phase of accelerating expansion driven by dark energy. This arrow of time, from order to disorder, from simplicity to complexity, from potential to actualization, shapes everything we observe in the cosmos. The very atoms in our bodies were forged in this expanding universe. The hydrogen emerged directly from the Big Bang. Heavier elements were manufactured in the hearts of stars, then scattered across space when those stars exploded as supernovae. These stellar remnants eventually coalesced into new stars, planets, and ultimately, life. We are, quite literally, made of stardust. Our existence a direct consequence of cosmic expansion and evolution. But as fundamental as expansion is to our existence, it also creates the border that limits our cosmic vision. As we look outward, we eventually reach regions where expansion exceeds the speed of light. These regions, though they exist and contain matter and energy like our own cosmic neighborhood, remain forever hidden from view. Their light, traversing the expanding space between us, fights a losing battle against cosmic stretching. Imagine dropping a letter into an emptying mailbox. If you drop it early enough, before the postal worker arrives, your message will be collected and delivered. Drop it too late, and it sits until the next collection. Now imagine that the mailbox itself is stretching, the distance between your letter and the top growing faster than the letter can move upward. No matter how long you wait, your message never reaches the top. It is trapped, forever unable to complete its journey. This is the fate of light from galaxies beyond our event horizon. Photons travel at their constant speed, but the space they must cross expands faster than they can traverse it. They make progress locally, moving through their immediate surroundings at light speed, but the finish line recedes faster than they advance. They are eternally in transit, never reaching their destination. This creates a fundamental limit to what we can observe. There are regions of the universe so distant that their light, even traveling at its tremendous speed for the entire age of the cosmos, has not yet reached us. These regions lie beyond our particle horizon, the maximum distance from which light could have reached us since the Big Bang. And there are regions even more profoundly disconnected, so distant that their light will never reach us, no matter how long we wait. These lie beyond our event horizon, permanently hidden by cosmic expansion. They exist, they evolve, they may even harbor life, but they remain forever invisible to us. Their stories untold, their light unseen. As strange as it may seem, these distant regions may contain observers like ourselves, gazing outward at their own observable universe, studying their own cosmic background radiation, charting their own galactic structures. They too would be bounded by their own cosmic horizons, able to see only a sphere with radius similar to our own. They would detect our galaxy only if it fell within their observable sphere, just as we see theirs only if they lie within ours. For galaxies sufficiently distant, there is no overlap between observable spheres. Observers in such galaxies would see entirely different portions of the universe, with no shared observable regions. They would develop cosmologies based on the evidence available to them, perhaps reaching similar conclusions about cosmic origin and evolution, but studying different collections of galaxies, different distributions of matter, different local structures. This is the cosmic shadow play created by expansion. The universe contains far more than any single observer can see. Each vantage point offers a unique perspective, a different slice of the greater whole. The true extent of the cosmos may far exceed what we can observe from Earth, perhaps even infinitely so. Yet expansion does not just hide, it also reveals. The very redshift that stretches light from distant galaxies provides clues about cosmic history. The relative abundances of elements, primarily hydrogen and helium, confirm the hot, dense, early state predicted by Big Bang theory. The cosmic microwave background, redshifted to microwave wavelengths, offers a direct image of the universe at 380,000 years of age. Through careful study of this expansion, cosmologists have pieced together a remarkably detailed history of the universe, from its first moments to the present day. We know that it began in an incredibly hot, dense state about 13.8 billion years ago. It expanded and cooled, forming hydrogen and helium in the first few minutes. It remained opaque for 380,000 years, then became transparent as electrons combined with nuclei to form the first atoms. The first stars emerged a few 100 million years later, ending the cosmic dark ages. Galaxies formed and evolved, merging and growing over billions of years. The expansion of the universe decelerated for about 9 billion years, then began to accelerate as dark energy became dominant. This acceleration continues today and is expected to persist into the indefinite future. This narrative, supported by multiple lines of evidence, represents one of the great achievements of modern science. Yet it is based entirely on what we can observe from our particular vantage point in space and time. It describes the history of our observable universe, the sphere with radius 46.5 billion light-years centered on Earth. What lies beyond remains speculation. The universe might extend far beyond our observable bubble, perhaps infinitely. It might contain regions with different physical properties, different distributions of matter, perhaps even different fundamental constants. These possibilities lie at the frontier of theoretical cosmology, the realm where observation meets mathematics and physics. The expansion of the universe, discovered less than a century ago, has transformed our understanding of the cosmos. It has replaced the static, eternal universe of earlier cosmologies with a dynamic, evolving cosmos with a definite beginning and a projected future. It has provided a framework for understanding everything from the origin of the elements to the formation of galaxies to the emergence of life itself. But it has also defined the limits of what we can know. It has created horizons, boundaries beyond which observation becomes impossible. It has divided the universe into the visible and the invisible, the accessible and the inaccessible, the known and the unknowable. As we gaze outward toward the silent border, we must remember that what we see is only a fraction of what exists. The observable universe, vast as it is with its billions of galaxies and trillions of stars, may be an infinitesimal portion of the whole. The true extent of the cosmos, hidden by expansion, may exceed our wildest imagination. The silent border grows with each passing moment. Every second, more galaxies cross the event horizon, their light no longer able to reach us. The observable universe contracts even as the actual universe expands, a paradox of cosmic vision. The border is not static but dynamic, a living boundary between the seen and the unseen. Every moment, more galaxies disappear, not into darkness, but into silence. When we speak of the universe, we must be precise about what we mean. Are we referring to all that exists? The totality of space, time, matter, and energy? Or do we mean what we can see, the sphere of visibility, centered on our planet? These two concepts, the actual universe and the observable universe, are profoundly different, separated by scales that may be truly infinite. The observable universe is simple to define, though difficult to comprehend in its vastness. It is everything we can potentially see, everything that could have sent light or other signals that have reached Earth since the beginning of time. Given the age of the universe, approximately 13.8 billion years, and the constant speed of light, one might expect this observable region to extend 13.8 billion light-years in all directions. But cosmic expansion complicates this picture. As light travels toward us, the space it traverses stretches. Galaxies that emitted light billions of years ago are now much farther away than they were when that light began its journey. Accounting for this expansion, the current radius of the observable universe is about 46.5 billion light-years. This makes the observable universe a sphere approximately 93 billion light-years in diameter, centered on Earth, or more precisely, centered on whoever is doing the observing. This sphere contains approximately 2 trillion galaxies, each home to billions of stars. The total number of stars within our observable universe is roughly 1 septillion, that is 1 followed by 24 zeros. Around these stars orbit countless planets, perhaps as many as 1 sextillion, a billion trillion worlds. These numbers overwhelm human comprehension, yet they represent only what we can potentially see. The actual universe, by contrast, encompasses everything that exists, whether visible to us or not. Its true extent remains unknown. It may be finite, but unbounded, like the surface of a sphere in 3 dimensions. It may be infinite, extending without limit in all directions. Current observations suggest that the universe is flat or very nearly so, which is consistent with an infinite extent, though it does not prove it. If the universe is indeed infinite, then the observable portion, vast as it is, represents exactly 0% of the whole. Any finite value divided by infinity equals 0. Our cosmic horizon, encompassing billions of light-years and trillions of galaxies, would be less than a drop in an endless ocean, less than a grain of sand on an infinite beach. Even if the universe is finite, its full extent may far exceed what we can observe. Some estimates based on the curvature of space suggest that if the universe does curve back on itself, completing a cosmic circle, that circle must be at least 250 times larger than our observable region. The actual universe would then be at least 250 times more voluminous than what we can see, containing 250 times more galaxies, stars, and planets. This disparity between the observable and the actual creates a profound limitation on our knowledge. No matter how powerful our telescopes become, no matter how sensitive our detectors, we will never be able to observe the entire universe if it extends significantly beyond our current horizon. The speed of light, combined with the finite age of the universe and the ongoing expansion of space, ensures that large portions of the cosmos remain forever hidden from view. This is not merely a practical limitation, but a fundamental one. It is not that we lack the technology or resources to see beyond our cosmic horizon, but that the laws of physics themselves prevent such observation. Even a civilization billions of years more advanced than our own, with technology we can scarcely imagine, would face these same constraints. The observable universe is all that any observer can potentially see, regardless of their location or technological prowess. The edge we see may not be the edge that exists. Our cosmic horizon is a perceptual boundary, not a physical one. Beyond it, the universe continues, filled with galaxies and stars, planets, and perhaps life, all evolving and existing in regions forever hidden from our view. This distinction between the observable and the actual universe has profound implications for our understanding of cosmic history and structure. The universe we observe appears remarkably uniform on the largest scales. Galaxies are distributed evenly throughout space, with no preferred direction or location. The cosmic microwave background, the afterglow of the Big Bang, shows the same temperature in all directions, to within 1 part in 100,000. This uniformity posed a puzzle for early cosmologists. If the Big Bang originated at a point, how could regions on opposite sides of the sky, separated by distances greater than light could travel in the age of the universe, have the same temperature? They could not have communicated or exchanged energy, yet they appear identical. The theory of cosmic inflation, proposed in the early 1980s, offers a solution. According to this theory, the universe underwent a brief but dramatic period of exponential expansion in its first fraction of a second. A tiny, causally connected region, smaller than a proton, expanded to macroscopic size, becoming the seed of our observable universe. Regions that now appear widely separated were once in close contact, explaining their similar properties. If inflation is correct, and most cosmologists believe it is based on multiple lines of evidence, then the actual universe is vastly larger than what we can observe. The inflationary expansion would have stretched space far beyond our cosmic horizon, creating a universe that may be effectively infinite in extent. Moreover, some versions of inflationary theory suggest that inflation never completely stops. While it ended in our region of space, allowing stars and galaxies to form, it continues elsewhere, constantly creating new regions of space that expand into their own universes. This eternal inflation would create a multiverse, an endless sea of cosmic bubbles, each with its own laws of physics, its own constants of nature, its own evolutionary history. In such a multiverse, our observable universe would be just one bubble among countless others, separated by distances so vast that they can never communicate. Each bubble would have its own observers, gazing out at their own cosmic horizons, studying their own cosmic microwave backgrounds, charting their own galactic structures. They would develop cosmologies based on the evidence available to them, perhaps reaching very different conclusions about the nature of reality. This picture becomes even more complex when we consider the possibility of curved space. Einstein's general theory of relativity, our best description of gravity and space-time, allows for different geometries of the universe as a whole. Space could be positively curved like the surface of a sphere, negatively curved like a saddle, or flat like a sheet of paper. Current observations strongly favor a flat universe, but they cannot definitively rule out a slight curvature. If the universe is positively curved, then traveling in a straight line would eventually bring you back to your starting point, just as circumnavigating the Earth returns you to where you began. The universe would be finite but unbounded, having no edge or border, yet containing a finite volume and a finite number of galaxies. If the universe is negatively curved, then space has a hyperbolic geometry, expanding more rapidly than a flat universe. Such a universe would most likely be infinite, extending without limit in all directions. Traveling in a straight line would never bring you back to where you started, no matter how far or how long you journeyed. A flat universe, the option most consistent with current observations, could be either finite or infinite. If flat and finite, it might have the topology of a torus, like the surface of a donut. Space would appear locally flat, but traveling far enough in certain directions would return you to your starting point. If flat and infinite, it would extend forever in all directions, containing an unlimited number of galaxies and stars. These geometries affect not just the overall structure of the universe, but also the relationship between the observable and the actual. In a positively curved universe, the observable portion might encompass a significant fraction of the whole, perhaps even all of it, if the curvature is strong enough. In a flat or negatively curved infinite universe, the observable region would be an infinitesimal portion of an endless cosmos. The shape of the universe also affects the trajectories of light rays and the apparent positions of distant objects. In a positively curved universe, parallel light rays eventually converge, making objects appear larger than they actually are. In a negatively curved universe, they diverge, shrinking the apparent size of distant sources. These effects provide a way to measure cosmic curvature, though current observations indicate that any such curvature must be extremely slight. Beyond these considerations of size and shape lies an even more profound question. Is the universe the same everywhere, or does it vary in its fundamental properties? The cosmological principle, a cornerstone of modern cosmology, assumes that the universe is homogeneous and isotropic on the largest scales, meaning it has the same properties in all locations and looks the same in all directions. This principle has been remarkably successful in explaining our observations, but it might not hold beyond our cosmic horizon. If inflation created a multiverse, different regions might have different laws of physics, different fundamental constants, different numbers of dimensions. What we regard as universal laws might be merely local bylaws, applicable only in our cosmic neighborhood. This possibility, while speculative, emerges naturally from theories like string theory, which suggests that our universe could have settled into one of many possible states during its early evolution. Other regions, beyond our observable horizon, might have settled into different states, creating a cosmic patchwork of varying physical laws. If true, this would mean that the actual universe is not just larger than the observable one, but qualitatively different in regions we cannot see. The uniformity we observe might be a local phenomenon, a consequence of our limited cosmic vision, rather than a universal truth. These considerations transform our understanding of the silent border. It is not just a boundary between the seen and the unseen, but potentially between different cosmic regimes, different physical realities, different evolutionary histories. The border is not merely where our vision fails, but where our understanding of the universe itself might need revision. Yet despite these profound limitations on our cosmic vision, we have learned an astonishing amount about the universe from the evidence available within our observable bubble. We know that it began in an incredibly hot, dense state about 13.8 billion years ago. We know that it expanded and cooled, forming hydrogen and helium in the first few minutes. We know that the first stars emerged after a few 100 million years, and galaxies evolved through collisions and mergers over billions of years. We know that our solar system formed about 4.6 billion years ago from the debris of previous stellar generations. We know that life emerged on Earth within its first billion years, and has evolved continuously since then. We know that humans are newcomers, present for only the last few 100,000 years of cosmic history. This knowledge, gleaned from studying our observable universe, represents one of the great achievements of human inquiry. Yet it pertains to less than 1% of what might exist, a cosmic field of view so narrow that it would be like trying to understand Earth by studying a single grain of sand. The observable universe, with its billions of galaxies and trillions of stars, is mind-bogglingly vast by human standards. The actual universe, potentially infinite in extent, transcends comprehension entirely. It is not just bigger than we imagine, but bigger than we can imagine, extending beyond not just our vision, but our conceptual frameworks. In this context, the silent border of the cosmos takes on new significance. It is not just the limit of what we can see, but the boundary of what we can know directly. Beyond it lies not just more of the same, but potentially different physics, different constants, different realities. The border marks not the edge of existence, but the edge of our particular bubble of existence, our cosmic neighborhood, in a potentially infinite expanse. This perspective humbles us, reminding us of the limits of human knowledge and the vastness of what remains unknown. Yet it also elevates us, highlighting the remarkable achievements of science in deciphering the cosmos from our tiny vantage point on a small planet orbiting an ordinary star in an ordinary galaxy. The observable universe is just a sphere of vision. The actual universe may be far bigger or infinite. The edge is not physical, it is perceptual. The cosmos continues, but we cannot follow. What might exist beyond our cosmic horizon? More galaxies, certainly, similar to those we observe within our visible sphere. The cosmological principle suggests that the distribution of matter should remain roughly constant, with galaxies clustered into filaments and sheets, separated by vast voids. Stars would continue to form and die, planets would orbit their suns, and the same physical processes we observe nearby would continue in distant regions. But if the universe is truly infinite, or even just vastly larger than our observable portion, then the possibilities multiply. Given enough space and enough combinations of matter, anything that is physically possible would not only occur, but would occur an infinite number of times. There would be other solar systems identical to ours, other Earths with identical histories, other copies of every human who has ever lived, differing only in the most minute details of their experiences. This is not mysticism or science fiction, but a direct consequence of infinity, combined with the quantum nature of the universe, which allows for only a finite, if immense, number of possible configurations of particles within any given volume of space. If the universe is infinite, then these configurations must repeat, just as a number chosen randomly from infinitely many digits must contain every possible finite sequence. Such cosmic repetition lies far beyond our observable horizon, separated from us by distances so vast that they can never be bridged, even by light traveling for the entire age of the universe. They exist, if the universe is infinite, but they remain forever beyond our ability to detect or confirm. The silent border of the cosmos thus separates us not just from more galaxies and stars, but from copies of ourselves, from worlds where history took different turns, from civilizations that evolved along different paths. It divides the potentially observable from the perpetually unseen, the knowable from the eternally unknown. Yet even within our observable bubble, we face practical limits to what we can see. Our most powerful telescopes can detect galaxies from the early universe, but not individual stars within them. We can observe the afterglow of the Big Bang, but not the event itself. We can infer the existence of dark matter and dark energy, but have yet to directly detect either. Our cosmic vision, while vast, remains incomplete even within its theoretical limits. These practical constraints remind us that the observable universe is itself a theoretical construct, the maximum volume from which signals could have reached us, given the age and expansion of the cosmos. The actually observed universe, the region we have directly studied with our instruments, is smaller still, limited by our technology and resources. As our abilities advance, we push the boundaries of the observed closer to the theoretical limits of the observable. New telescopes, like the James Webb Space Telescope, peer deeper into space and further back in time, revealing galaxies from when the universe was less than 5% of its current age. Gravitational wave detectors open new windows on the cosmos, allowing us to perceive events invisible to traditional astronomy. Neutrino observatories capture particles that have traveled from the cores of stars and supernovae, carrying information from regions opaque to light. These technological advances expand our cosmic vision, but they cannot break through the fundamental barrier created by the speed of light and the age of the universe. No matter how powerful our instruments become, regions beyond our particle horizon remain invisible, their light still en route, their stories untold. And regions beyond our event horizon remain permanently beyond reach, their light unable to overcome the expansion of space, their existence knowable only through theory and inference. The observable universe thus becomes our cosmic island, a sphere of visibility in a potentially endless sea. Within this island, we can observe and measure, test theories and predictions. Beyond it, we can only speculate, guided by our understanding of physics, but unable to confirm our conjectures through direct observation. This island, our observable universe, has a horizon, a circular boundary, where the known meets the unknown, where light reaches us from the dawn of time, where galaxies recede at the speed of light. This horizon is not a physical edge, but a perceptual one, a limit to our cosmic vision, rather than a boundary in space itself. Stand on the shore of an ocean, and you see a circular horizon where sea meets sky. This is not the edge of the ocean, but the limit of what you can see from your height above the water. Move to a higher vantage point, and the horizon expands, revealing more ocean beyond. The cosmic horizon works similarly, except that our vantage point is fixed by the fundamental laws of physics. We cannot see beyond our particle horizon because light from there has not had time to reach us. We cannot see beyond our event horizon because light from there never will reach us due to cosmic expansion. The actual universe continues beyond these horizons, filled with galaxies and stars, planets and perhaps life, all evolving and existing in regions forever hidden from our view. The cosmos does not end at the limits of our vision. It extends beyond, perhaps without limit, a vast territory unknown and unknowable to any single observer. This disparity between the observable and the actual universe presents a profound challenge to science. How do we develop and test theories about regions we cannot observe? How do we distinguish between models that make identical predictions within our observable bubble but differ in their descriptions of what lies beyond? How do we avoid the anthropic trap of assuming that what we observe must be typical of the universe as a whole? In our journey toward the silent border of the cosmos, we must understand the nature of cosmic horizons. These are not physical boundaries, but limits to what can be observed, thresholds beyond which information cannot pass. They define the observable universe, shaping our cosmic perspective and constraining our knowledge of what lies beyond. Two primary horizons circumscribe our cosmic vision: the particle horizon and the event horizon. Though similar in concept, they define fundamentally different boundaries with profound implications for our understanding of the universe. The particle horizon marks the limit of what we can currently see. It encompasses all regions of space from which light or other signals could have reached us since the beginning of time. Given the age of the universe, approximately 13.8 billion years, and the constant speed of light, this horizon might seem simple to calculate. Light travels approximately 9.5 trillion kilometers in 1 year, so multiplying this by the age of the universe should give the radius of our observable bubble. But cosmic expansion complicates this calculation. As light travels toward us, the space it traverses stretches. This affects both the distance the light must cover and the wavelength of the light itself. A photon emitted by a distant galaxy billions of years ago has traveled through space that has been continuously expanding throughout its journey. The galaxy itself has moved much further away since that photon began its voyage. Accounting for this expansion, the current radius of the particle horizon is about 46.5 billion light-years. This makes the observable universe a sphere approximately 93 billion light-years in diameter, centered on Earth, or, more precisely, centered on any observer. For each vantage point in the cosmos has its own unique particle horizon. This horizon is not static but dynamic, expanding with time. As the universe ages, light from increasingly distant regions has time to reach us. With each passing second, our particle horizon encompasses a slightly larger volume of space, bringing previously invisible regions into view. If we could somehow live for billions of years, we would see this horizon steadily expand, revealing new galaxies, new structures, new portions of the cosmic web. But there is a limit to this expansion, a boundary beyond which lies territory forever hidden from view. This is the cosmic event horizon, the second great limit to our cosmic vision. While the particle horizon defines what we can see now, the event horizon defines what we will ever be able to see, no matter how long we wait. The event horizon exists because of the accelerating expansion of the universe. Discovered in 1998 through observations of distant supernovae, this acceleration is attributed to dark energy, a mysterious force that acts like anti-gravity on cosmic scales. As dark energy pushes space apart with ever-increasing efficiency, galaxies recede from each other at ever-increasing rates. Those sufficiently distant move away faster than light, not because they break Einstein's cosmic speed limit, but because the space between expands rapidly enough to carry them beyond light speed. For galaxies beyond a certain distance, roughly 16 billion light-years in the current era, this superluminal recession ensures that their light will never reach us, no matter how long we wait. As these photons travel toward Earth, the space they must cross expands faster than they can traverse it. They are like swimmers fighting against a current that flows faster than they can stroke, perpetually losing ground despite their constant motion. This cosmic event horizon creates a boundary beyond which events are forever hidden from our view. Not because signals from these regions have not had time to reach us yet, but because they never will. The expansion of space ensures that these regions remain permanently beyond our cosmic sight, their light eternally chasing a target that recedes faster than it can pursue. Unlike the particle horizon, which expands with time, the cosmic event horizon contracts as the universe ages. Galaxies that are visible today will, in the distant future, accelerate beyond our cosmic sight as dark energy's influence grows stronger. Their light, once able to reach us, will find itself fighting against an increasingly rapid expansion of space. A battle it must eventually lose. In the far future, trillions of years from now, observers in the Milky Way, or whatever galaxy our descendants might inhabit, will see a very different night sky. Most galaxies will have accelerated beyond the event horizon, their light unable to counteract the expansion of space. The observable universe will consist primarily of the local group, a collection of galaxies gravitationally bound together, isolated in an otherwise empty and darkening cosmos. For these future observers, the evidence for the Big Bang, for a universe teeming with galaxies, for cosmic expansion itself, will have faded away. The cosmic microwave background will be redshifted to such long wavelengths as to be undetectable. Distant galaxies will be gone from view. If intelligence evolves at this late cosmic epoch, it might conclude that the universe consists only of a small collection of galaxies in an otherwise static, eternal void. This thought experiment reveals a profound truth about cosmic horizons. They not only limit what we can see, but they shape what we can infer, what theories we can develop, what conclusions we can draw about the nature of the cosmos. Our understanding of the universe is bounded not just by our technology and intelligence, but by our particular vantage point in space and time. Between these twin horizons, the particle horizon that limits what we can see now, and the event horizon that limits what we will ever see, lies a shell of space from which light is still en route to Earth. Photons from this region were emitted after the Big Bang, but have not yet completed their journey to our telescopes. Given enough time, light from this intermediate zone will eventually reach us, revealing galaxies and structures currently hidden from view. But for regions beyond the event horizon, silence is permanent. No signal will ever cross that boundary. No light will ever breach that wall. These regions are not just unseen, but unseeable, causally disconnected from our own. They exist, they evolve, they may contain galaxies and stars, planets, and perhaps life, but their stories remain forever untold to observers in our cosmic neighborhood. This causal disconnection has profound implications for our understanding of the cosmos. Events beyond our event horizon cannot affect our future. No matter what happens there, no matter what wonders might unfold or catastrophes occur, they will remain forever unknown to any observer in our region of space. It is as if these regions exist in separate universes, connected in principle by the shared origin of the Big Bang, but now evolving independently, each blind to the other's fate. The twin horizons, particle and event, define the limits of our cosmic perception, the boundaries of our observable bubble in the greater sea of existence. They are not physical edges, but perceptual ones, limits imposed by the fundamental laws of physics, by the finite speed of light, the finite age of the universe, and the ongoing expansion of space. Yet these horizons are not the only ones that shape our cosmic understanding. Black holes, those regions where gravity becomes so intense that not even light can escape, possess their own event horizons. These are true points of no return, boundaries in space-time beyond which information cannot escape to the outside universe. Once something crosses a black hole's event horizon, it is forever lost to external observers, its fate sealed by the inexorable pull of gravity. Black hole horizons differ from cosmic horizons in crucial ways. The cosmic event horizon is observer-dependent, varying with location. Each galaxy, each planet, each particle in the universe has its own unique cosmic horizons, its own observable bubble centered on its position. But a black hole's event horizon is absolute, a feature of space-time itself, the same for all observers, regardless of their location or motion. Moreover, crossing the cosmic event horizon has no local effect. A galaxy that accelerates beyond our cosmic sight continues to exist as before, its stars shining, its planets orbiting, its potential inhabitants unaware that they have crossed a boundary significant only to distant observers. But crossing a black hole's event horizon is a one-way journey from which there is no return, a passage into a region where space and time themselves behave differently, where all trajectories lead inevitably toward the central singularity. Despite these differences, both types of horizons share a common feature. They divide the universe into regions that can communicate and regions that cannot, into the accessible and the inaccessible, the observable and the unobservable. They create boundaries not in space itself, but in the flow of information, in the causal connections that link events across the cosmos. The universe also contains another type of horizon, one that existed only in its earliest moments. The cosmic microwave background, the oldest light we can detect with conventional telescopes, comes from when the universe was just 380,000 years old. Before that time, the cosmos was opaque, filled with a hot, dense plasma that scattered photons before they could travel far. This opacity created a visual horizon, a wall of fog beyond which electromagnetic observations cannot penetrate. But this early universe horizon is not absolute. Other messengers, like neutrinos and gravitational waves, can carry information from earlier cosmic epochs. Neutrinos, nearly massless particles that rarely interact with matter, decoupled from the primordial plasma when the universe was just 1 second old. Detecting these primordial neutrinos would open a window onto a much earlier phase of cosmic evolution, though their extremely low energy makes such detection extraordinarily challenging with current technology. Gravitational waves, ripples in the fabric of space-time caused by the acceleration of massive objects, offer another potential window into the early universe. Unlike electromagnetic radiation, gravitational waves are not scattered or absorbed by matter. They propagate freely through the densest environments, carrying information directly from the events that generated them. Future gravitational wave observatories might detect echoes from cosmic inflation, the exponential expansion thought to have occurred in the first fraction of a second after the Big Bang. These alternative messengers, neutrinos and gravitational waves, allow us to probe beyond the conventional visual horizon of the early universe. They push back the limits of our cosmic perception, revealing events and processes otherwise hidden from view. But they cannot breach the fundamental horizons set by the speed of light and the expansion of space. The particle horizon and the event horizon remain ultimate boundaries, limits beyond which no information of any kind can reach us. The various horizons of the universe, particle and event, black hole and early universe, all share a common theme. They mark boundaries of information flow, limits to causal connection, thresholds beyond which events become unobservable or unknowable. They divide the cosmos into regions that can communicate and regions that cannot, into the visible and the invisible, the accessible and the inaccessible. This division has profound implications for our understanding of the universe. It means that our observable bubble, vast as it is with its billions of galaxies and trillions of stars, may be an infinitesimal portion of what exists. It means that the laws and constants we measure locally may not apply universally. It means that events beyond our horizons, events that may profoundly shape the larger cosmos, remain forever hidden from our view. Consider the implications of this for a moment. There may be regions of the universe where galaxies form differently, where stars burn at different rates, where the balance of fundamental forces differs from what we measure in our cosmic neighborhood. There may be regions with different histories, different structures, different possibilities. All of this may exist, yet remain forever beyond our ability to observe or confirm. This is not mere speculation. If cosmic inflation occurred as many cosmologists believe, creating a vast or infinite universe from a tiny quantum fluctuation, then regions far beyond our horizon would have different initial conditions, different quantum fluctuations, different evolutionary paths. The differences might be subtle or profound, ranging from minor variations in the distribution of matter to fundamental changes in the constants of nature. In some versions of inflationary theory, inflation never completely stops. While it ended in our region, allowing stars and galaxies to form, it continues elsewhere, constantly creating new regions of space that expand into their own universes. This eternal inflation would create a multiverse, an endless sea of cosmic bubbles, each with its own laws and constants, its own evolutionary history, its own possibilities. In such a multiverse, our horizons would not just mark the limits of our vision, but the boundaries of our particular cosmos, our bubble of existence in a much larger reality. What lies beyond would not be more of the same, but potentially different physics, different rules, different realities altogether. These ideas push at the boundaries of science, forcing us to consider what constitutes evidence, what qualifies as knowledge, what separates science from speculation. They remind us that our cosmic understanding, impressive as it is, remains bounded by fundamental limits, constrained by our particular vantage point in space and time. Yet despite these limitations, we continue to explore, to observe, to theorize. We push our instruments to their limits, extracting every bit of information from the light that reaches Earth. We develop mathematical models that extend beyond what we can see, guided by the patterns we observe within our horizon. We test these models against new observations, refining our understanding of the cosmos step by step. In this quest, cosmic horizons serve not just as limits, but as guides, reminding us of the vastness beyond our vision, challenging our imagination and our intellect. They tell us that the universe is not just what we see, but what exists, whether visible to us or not. They remind us that reality does not conform to our ability to perceive it, that the cosmos continues whether we can observe it or not. The particle horizon, currently about 46.5 billion light-years away, marks the edge of our current visibility. Beyond it lie galaxies and stars whose light has not yet had time to reach us. With each passing moment, this horizon expands slightly, bringing new regions into view. Given enough time, these distant galaxies will become visible, their light finally completing its journey across the expanding universe. But the cosmic event horizon, currently about 16 billion light-years away, marks a more profound boundary. Beyond it lie regions from which light will never reach us, no matter how long we wait. The expansion of space ensures that these regions remain forever hidden, their stories untold, their existence known only through theory and inference. As the universe ages and expansion accelerates, the event horizon draws closer, shrinking our potentially observable bubble, even as the actual universe continues to expand. In the far future, all galaxies not bound to our local group will disappear from view, accelerated beyond our cosmic sight by dark energy's relentless push. The observable universe will contract to a small island of galaxies in an otherwise invisible cosmos. For future observers, should any exist in this distant epoch, the evidence for a vast universe filled with galaxies, for cosmic expansion, for the Big Bang itself, will have faded away. The cosmic microwave background will be redshifted to undetectable wavelengths. Distant galaxies will be gone from view. The universe will appear static and eternal, a small collection of galaxies in an otherwise empty void. This eventual isolation highlights another aspect of cosmic horizons. They not only limit what we can see, but also what evidence is available to us, what theories we can test, what conclusions we can draw about the nature of the cosmos. Our understanding of the universe is bounded not just by our intelligence and technology, but by our particular moment in cosmic history. We live in what future cosmologists might regard as a privileged epoch, a time when the evidence for cosmic expansion, for the Big Bang, for dark energy is readily observable. We can detect the cosmic microwave background, measure the redshifts of distant galaxies, observe the accelerating expansion of space. These observations allow us to reconstruct between the galaxies lies emptiness, vast voids, enormous bubbles of near-nothingness that stretch for hundreds of millions of light-years. These cosmic deserts contain so little matter that if Earth orbited a star in their center, our night sky would appear almost empty. We would see perhaps a handful of distant galaxies where we now see thousands, and might believe the universe to be a lonely, barren place. These great voids are not completely empty. Tenuous wisps of hydrogen gas float within them, so diffuse that they would be considered a perfect vacuum by laboratory standards on Earth. Occasional stray stars, ejected from their galaxies by gravitational interactions, drift through the darkness, their light too faint to be seen from afar. Invisible dark matter permeates these regions, its presence detectable only through its gravitational effects on the larger cosmic structure. But compared to the brilliant congregations of stars we call galaxies, these voids are silent and dark, empty stages upon which little cosmic drama unfolds. They are the negative space of the universe, defining the cosmic web by their very absence, shaping the distribution of matter through their gravitational influence. The largest known void, the Boots void, spans approximately 330 million light-years. If placed at its center, our most powerful telescopes would detect only a handful of galaxies in what appears to us as a sky filled with thousands. At roughly 10,000 times less dense than the cosmic average, it contains so little matter that astronomers initially doubted its existence when it was discovered in 1981. Another massive empty region, the Eridanus supervoid, stretches 500 million light-years across. Its presence corresponds with a notable cold spot in the cosmic microwave background, suggesting that it may have formed from a primordial fluctuation in the earliest moments of the universe. This connection between the largest structures we observe today and quantum fluctuations from the Big Bang illustrates the remarkable continuity of cosmic evolution, from microscopic beginnings to macroscopic ends. The CMB cold spot, as it is called, is approximately 70% emptier than average, creating a temperature depression of about 70 microkelvin in the otherwise remarkably uniform cosmic microwave background. This slight cooling occurs because photons from the early universe lose energy as they cross large voids, a phenomenon known as the integrated Sachs-Wolf effect. The light must climb out of a gravitational potential well, expending energy and shifting to longer, cooler wavelengths in the process. These vast voids form naturally as the universe evolves. In the early cosmos, matter was distributed almost uniformly, with only tiny fluctuations in density caused by quantum effects during inflation. These slight overdensities attracted more matter through gravity, while underdense regions lost material to their denser surroundings. Over billions of years, this process amplified the initial variations, creating the cosmic web of filaments, clusters, and voids we observe today. The voids expand faster than the universe as a whole, as matter flows away from their centers toward the surrounding filaments and walls. They grow not just through cosmic expansion, but through evacuation, becoming increasingly empty as time proceeds. Eventually, they merge with neighboring voids, creating ever larger empty regions as the cosmic web evolves. These great empty spaces serve an essential cosmic purpose. They are the negative imprint of the universe's large-scale structure, the background against which the luminous matter clusters and collects. Without voids, there would be no filaments, no clusters, no complex cosmic web. The universe would be uniform and featureless, lacking the rich structure that ultimately allowed matter to condense into galaxies, stars, and planets. The silence of these voids is not absolute, but relative. They contain little matter compared to their surroundings. Few sources of electromagnetic radiation, minimal cosmic activity. Their silence comes not from complete emptiness, but from sparseness, from the vast distances between objects, from the nearly imperceptible whisper of their meager contents against the roaring chorus of galactic life. This silence extends beyond voids to the spaces between stars within galaxies, and beyond galaxies to the spaces between galaxy clusters. The average distance between stars in our Milky Way is approximately 4 light-years. A gulf so vast that light, traveling at 300,000 kilometers per second, requires years to cross it. The space between neighboring galaxies in a cluster might span millions of light-years, and the distance between clusters can reach tens or hundreds of millions of light-years. These enormous separations create a fundamental silence in the cosmos, a disconnect between objects that might otherwise interact more directly. Signals weaken with distance, diminishing as the square of the separation. A star twice as far away appears 4 times dimmer. A galaxy 10 times more distant seems 100 times fainter. The vast majority of the universe lies too far from any given point to be seen clearly. Its light too dim, its signals too weak to register strongly. This is the paradox of cosmic silence. The universe contains hundreds of billions of galaxies, each home to hundreds of billions of stars. Yet from any given location, most of this vast array appears faint or invisible, lost in the immensity of space, silenced by sheer distance. The cosmos teems with activity, yet most locations experience only a whisper of this cosmic symphony, the rest rendered inaudible by distance and time. Even the signals that do reach us have been transformed by their journey. Light from distant galaxies is redshifted, stretched to longer wavelengths by cosmic expansion. What began as ultraviolet or visible light might arrive as infrared or radio waves, changed in character by billions of years of transit through expanding space. The cosmic microwave background, once a brilliant glow at thousands of degrees, now reaches us as faint microwaves barely 3 degrees above absolute zero, a whisper of its original intensity. Time itself contributes to the cosmic silence. The light we receive from distant objects shows them not as they are now, but as they were when that light began its journey. We see the Andromeda Galaxy as it existed 2.5 million years ago, the Virgo cluster as it was 50 million years in the past, the most distant observable galaxies as they appeared more than 13 billion years ago. We observe not a simultaneous universe, but a historical one, a collection of images from different epochs arrayed in space around us. This temporal disconnect means that the universe we observe does not exist as such. The most distant galaxies we see may no longer exist in the form we observe, having merged or evolved or receded beyond our cosmic horizon in the billions of years since their light began its journey to Earth. The cosmos we study is a ghost, a historical record, silent not just because of distance, but because of time. As we look outward from Earth, we also look backward in time, seeing progressively earlier epochs of cosmic history. At the limits of our vision, we observe not just the most distant objects, but the earliest ones. The first stars and galaxies emerging from the cosmic dark ages, hundreds of millions of years after the Big Bang. Beyond that lies the cosmic microwave background, the afterglow of the Big Bang itself, the oldest light we can detect with conventional telescopes. This visual time machine creates another form of cosmic silence. We cannot see what distant regions look like now, only what they looked like in the past. Their present state remains hidden, silent to our instruments, accessible only through inference and modeling. The further we look, the greater this silence becomes, the more profound the disconnect between what we see and what actually exists. This silence deepens still further when we consider the accelerating expansion of the universe. Galaxies beyond our event horizon, approximately 16 billion light-years in the current era, recede faster than light due to cosmic expansion. Their signals will never reach us, no matter how long we wait. These regions are not just temporarily silent, but permanently so, forever beyond our ability to observe or communicate with directly. As dark energy drives cosmic acceleration, this event horizon contracts, encompassing an ever smaller portion of the actual universe. Galaxies visible today will, in the distant future, accelerate beyond our horizon, their signals no longer able to reach us. The observable universe shrinks even as the actual universe expands, a paradox of cosmic vision. The silence grows with each passing eon, encompassing an increasingly large fraction of all that exists. In the far future, trillions of years from now, Only the local group of gravitationally bound galaxies will remain visible from Earth or its cosmic vicinity. All other galaxies will have accelerated beyond our event horizon, their light unable to overcome the expansion of space. The cosmos will appear static and limited, a small collection of aging galaxies in an otherwise empty void. The evidence for a vast universe, for cosmic expansion, for the Big Bang itself, will have faded away, leaving future observers with a much diminished view of cosmic reality. The silence of cosmic voids thus offers a preview of the ultimate fate of the observable universe. It shows us what the cosmos will become in its dotage, a vast emptiness punctuated by isolated islands of matter, separated by gulfs too vast to bridge even with light. The silence of voids today becomes the silence of the universe tomorrow, as cosmic acceleration drives galaxies beyond our horizon, as stars burn out, as matter itself eventually decays. Yet even this profound and growing silence is not the deepest form of cosmic quiet. Beyond our event horizon lies a region permanently invisible to us, a territory whose evolution proceeds without our witness, whose stories remain forever untold from our perspective. This is the ultimate cosmic silence, not of distance or time or vacancy, but of causal disconnection, of regions forever hidden from our view. This silence is not empty of content or activity. These regions beyond our horizon may contain galaxies and stars, planets and perhaps life, all evolving and existing just as in our observable bubble. But from our perspective, they might as well not exist, for no signal from them will ever reach us. No light or information of any kind can cross the boundary created by accelerating cosmic expansion. Similarly, no signal from us can ever reach them. We are as silent to potential observers beyond our horizon as they are to us. This symmetry of silence, this mutual inaudibility, divides the universe into causally disconnected regions, cosmic islands that evolve independently, despite their shared origin in the Big Bang. What happens here cannot affect what happens there, and vice versa, a cosmic isolation more profound than mere distance. The silence of cosmic voids, the silence of intergalactic space, the silence beyond our cosmic horizon, these quiet regions comprise the vast majority of the universe. The luminous matter we observe, the stars and galaxies that emit the light we study, occupy only a tiny fraction of cosmic volume. The universe is mostly silent, mostly dark, mostly empty, by any standard we might apply. This prevalence of silence shapes our perception of the cosmos. We focus on the luminous, the energetic, the structured, because these are what we can observe directly. But the silent majority of the universe, the voids and spaces, the regions beyond our horizon, these too are part of cosmic reality, perhaps the dominant part. They shape the evolution of the visible universe through their gravitational influence, their expansion, their very existence. The silence is not just absence but presence, not just emptiness, but fullness of a different kind. The voids contain dark energy, that mysterious force driving cosmic acceleration. They host tenuous gases and occasional stray stars. They are permeated by neutrinos, those ghostly particles that rarely interact with matter, and by cosmic microwave background photons, the afterglow of the Big Bang itself. They are not nothing, but something different, a form of cosmic existence characterized by sparseness rather than density, by quiet rather than activity. Even the vacuum of space itself is not truly empty, but seethes with quantum fluctuations, with virtual particles popping in and out of existence, with fields that permeate all of space-time. In quantum field theory, the vacuum is a dynamic state, the lowest energy configuration of fields, not the absence of anything. The silence of cosmic voids is thus not absolute, but relative, not the silence of non-existence, but the quiet background against which the louder cosmic processes stand out. The Boots void and other vast empty regions may seem silent and barren compared to galaxy clusters, but they too have a cosmic role to play. They are not just the absence of structure, but part of structure itself, the valleys that define the mountains, the shadows that reveal the light. Without voids, there would be no cosmic web, no filaments, no clusters, no complexity at the largest scales. As we ponder these great silent places, we must reconsider our notion of emptiness itself. Is a region devoid of visible matter truly empty? Does the presence of fields, of quantum fluctuations, of dark energy, of occasional atoms qualify as fullness? Where do we draw the line between something and nothing, between silence and sound? These questions are not merely philosophical but physical, with implications for our understanding of the cosmos. The nature of the vacuum, of dark energy, of quantum fields, these fundamentally determine the fate of the universe, its expansion and evolution, its ultimate destiny. The silent places that seem empty to casual observation may hold the keys to the deepest cosmic mysteries. The silence of cosmic voids also offers an opportunity for certain kinds of observation. Radio astronomers seek these quiet regions to detect faint signals that might be drowned out by the electromagnetic noise of galaxies. The relative emptiness of voids makes them ideal windows for studying the diffuse intergalactic medium, the tenuous gas that permeates all of space. The absence of intervening matter allows clearer lines of sight to distant objects, minimizing absorption and scattering of light. This illustrates another aspect of cosmic silence. It is not just the absence of signal, but the absence of noise. Not just emptiness, but clarity. Not just void, but opportunity. The quiet places of the cosmos offer their own form of cosmic revelation, a different perspective on the universe, a window onto phenomena that might otherwise remain hidden. As we journey toward the silent border of the cosmos, these great voids serve as waypoints, vast empty gulfs between the islands of galactic light. They remind us that the universe is mostly space, mostly silence, mostly vacuum by our conventional standards. The luminous matter we observe, the stars and galaxies that emit the light we study, represent only a tiny fraction of what exists, small beacons in an otherwise dark and quiet cosmos. This realization transforms our perception of the universe. We are not surrounded by fullness, but by emptiness, not by noise, but by silence, not by density, but by sparseness. The average density of matter in the observable universe is approximately 6 hydrogen atoms per cubic meter, a vacuum more perfect than anything we can create in laboratories on Earth. If we could somehow compress all the matter in the observable universe, eliminating the empty space between particles, it would fit within a volume smaller than a sugar cube. This cosmic emptiness exists not just between galaxies but within them. Stars occupy a tiny fraction of galactic volume, separated by vast gulfs of nearly empty space. Our solar system is mostly vacancy, with planets as small specks in an otherwise empty stage. Even matter itself is mostly empty, with subatomic particles occupying a negligible portion of atomic volume. At every scale, from the subatomic to the cosmic, emptiness predominates over fullness, silence over sound. Yet this emptiness teems with fields and forces, with energy and potential. The vacuum of space is permeated by the electromagnetic field, the gravitational field, the quantum fields of the standard model of particle physics. Dark energy fills every cubic centimeter of the cosmos, driving its acceleration with its negative pressure. Neutrinos and cosmic microwave background photons journey through the void, nearly undetectable but nevertheless present, silent messengers from earlier cosmic epochs. This tension between emptiness and fullness, between silence and signal, defines our understanding of the cosmos. The universe is both emptier than we imagine, with vast voids and spaces between all structures, and fuller than we perceive, with fields and forces and particles that escape direct observation, but nevertheless influence cosmic evolution. As we journey toward the silent border of the cosmos, we encounter a universe not just vast in space, but deep in time. The light that reaches our telescopes from distant galaxies has traveled for billions of years across the expanding cosmos. We see these ancient beacons not as they are today, but as they were when their light began its long journey to Earth. This temporal aspect of cosmic observation creates a fundamental disconnect. The most distant galaxies visible to our instruments, those at the edge of our observable universe, appear to us as they existed more than 13 billion years ago, when the universe was in its infancy. Their present state remains unknown and unknowable, hidden by the finite speed of light and the vast gulfs of space that separate us. These distant galaxies differ markedly from those nearby. They appear smaller, more chaotic, bluer in color, forming stars at rates hundreds of times higher than the Milky Way. They show us the universe in its youth, when galaxies were still assembling, when the cosmic drama of structure formation was in full swing. They are cosmic time capsules, preserving the conditions of the early universe for our telescopes to discover billions of years later. But many of these ancient galaxies, whose light reaches us from the dawn of cosmic time, have already vanished from our observable universe. Not because they ceased to exist, but because cosmic expansion has carried them beyond our event horizon, the boundary beyond which signals can never reach us. Their light, which once could bridge the gulf between us, now fights a losing battle against the accelerating expansion of space. This is the first sense in which galaxies fade from our cosmic view. Objects visible in the past may no longer be observable today, not because they disappeared, but because the expansion of space has pushed them beyond our cosmic horizon. The observable universe contracts even as the actual universe expands, a paradox of cosmic vision. Galaxies that were once within our observable bubble may now lie beyond it, their signals unable to overcome the relentless stretching of space. To understand this phenomenon, imagine a distant galaxy whose light has taken 12 billion years to reach us. We see it as it existed 12 billion years ago, when the universe was less than 2 billion years old. During those 12 billion years, the galaxy has moved farther away due to cosmic expansion. If it now lies beyond our event horizon, approximately 16 billion light-years in the current era, its present light will never reach us. We see its past, but will never observe its future. This process continues today. Galaxies currently at the edge of our observable universe will, in the future, accelerate beyond our cosmic view. Their light, currently able to reach us after billions of years of travel, will eventually find itself fighting against an expansion of space too rapid to overcome. These galaxies will fade from our cosmic vision, not through any change in their intrinsic brightness, but through their superluminal recession caused by cosmic expansion. In the distant future, billions to trillions of years from now, only galaxies in our local group, those bound to the Milky Way by gravity, will remain visible. All other galaxies will have accelerated beyond our cosmic horizon, their light unable to reach observers in our cosmic vicinity. The observable universe will contract to a small island of galaxies in an otherwise invisible cosmos. For future astronomers, should any exist in this distant epoch, the evidence for a vast universe filled with galaxies, for cosmic expansion, for the Big Bang itself, will have faded away. The cosmic microwave background will be redshifted to undetectable wavelengths. Distant galaxies will be gone from view. The universe will appear static and eternal, a small collection of galaxies in an otherwise empty void. This eventual isolation represents the second sense in which galaxies fade from view. Not only do distant objects accelerate beyond our cosmic horizon, but the evidence for a larger cosmos gradually disappears. The observable universe not only contracts, but simplifies, losing the clues that allow us today to reconstruct cosmic history and structure. The universe forgets itself, its past hidden by its own expansion, its history erased by time. But galaxies fade in a third sense as well, more gradual but equally profound. Stars do not shine eternally but live finite lives, burning through their nuclear fuel before ending as white dwarfs, neutron stars, or black holes. The most massive stars, though brightest, live shortest, exploding as supernovae after just a few million years. Less massive stars burn longer, with mid-sized stars like our Sun shining for about 10 billion years, and the smallest red dwarfs potentially lasting for trillions. Yet even these longest-lived stars must eventually exhaust their nuclear fuel. In about 1 to 10 trillion years, depending on their exact mass, the last stars will flicker out, leaving only their dense remnants. Galaxies, those great cosmic metropolises filled with billions of brilliant stars, will grow dark, their light fading not through distance or cosmic expansion, but through the inevitable exhaustion of nuclear fuel. This stellar extinction begins with the most massive stars, those giants tens to hundreds of times more massive than our Sun. These cosmic behemoths burn through their hydrogen at prodigious rates, converting it to helium and heavier elements through nuclear fusion. Despite their enormous fuel reserves, their high consumption rates limit their lifespans to mere millions of years, a cosmic eye blink compared to the 14 billion year age of the universe. When these massive stars die, they do so spectacularly, exploding as supernovae or hypernova, briefly outshining their entire host galaxies. These cataclysmic events scatter newly forged elements into space, enriching the interstellar medium with carbon, oxygen, iron, and other elements essential for plant life. But they also represent the first step in the fading of galaxies, as their brightest members burn out early, like candles consuming themselves at both ends. Mid-sized stars, like our Sun, follow a different path. After exhausting the hydrogen in their cores, they expand into red giants, fusing helium into carbon and oxygen. Eventually, they shed their outer layers as planetary nebulae, leaving behind dense white dwarfs composed primarily of carbon and oxygen. These stellar corpses initially glow white-hot, but with no ongoing nuclear fusion, they gradually cool over billions of years, fading from white to yellow to red, and eventually to black, invisible cinders in the cosmic night. The smallest stars, red dwarfs with less than half the sun's mass, burn their fuel most efficiently. By convecting their entire volume, they use all their hydrogen for fusion, not just their cores. These cosmic misers can shine for up to 10 trillion years, outlasting all other stars. But even they must eventually fade, becoming white dwarfs, and then cooling to invisibility over countless additional billions of years. As stars of different masses extinguish at different rates, galaxies gradually dim. The bright blue light of massive stars fades first, leaving the yellower glow of Sunday-like stars, then the ruddy light of red dwarfs, and finally darkness. Galaxies do not maintain their current appearance, but evolve, growing redder and dimmer as their stellar populations age and die without sufficient new star formation to replace them. This process has already begun. The rate of star formation in the universe peaked about 10 billion years ago and has been declining ever since. Today, the cosmos forms stars at only about 10% of its peak rate. Many galaxies, particularly massive ellipticals, have already ceased star formation entirely, their gas reserves exhausted or heated to temperatures too high for stellar birth. These red and dead galaxies glow with the ruddy light of aging low-mass stars, their bright blue giants long since departed from the cosmic stage. In about 100 billion years, the gas needed for new star formation will be nearly depleted throughout the observable universe. Occasional supernovae may still enrich the interstellar medium, and rare collisions between stellar remnants might create new stars. But these isolated events cannot maintain galaxies at their current brilliance. The cosmic fire gradually dims as existing stars burn out, without replacement. By 1 trillion years after the Big Bang, normal star formation will have ceased entirely. Only red dwarfs and stellar remnants will remain, the former still fusing hydrogen at their miserly rates, the latter cooling inexorably toward cosmic zero. Galaxies will appear as diffuse collections of faint red stars, a dim shadow of their former glory. As red dwarfs finally exhaust their fuel over the subsequent trillion years, galaxies fade to near invisibility, detectable only by the slight gravitational lensing they induce in light from other fading galaxies. The universe enters its degenerate era, dominated by white dwarfs, neutron stars, and black holes, objects that emit little or no electromagnetic radiation detectable by conventional means. This dimming combines with cosmic expansion to accelerate the fading of distant galaxies from view. Light from remote objects, already stretched and dimmed by the expansion of space, grows fainter still as their stars burn out and die. The combined effect empties the visible universe faster than either process alone, a synergy of extinction that gradually erases the cosmic landscape from view. But stars and galaxies do not merely fade, they also vanish through other mechanisms. As galaxies orbit within clusters, Gravitational interactions occasionally eject individual stars or even small stellar groups. These cosmic exiles fly off into intergalactic space, lost from their parent galaxies, destined to wander the void alone or in small groups. Over billions to trillions of years, this process gradually dissolves galaxies, scattering their stars into the vast emptiness between larger structures. Meanwhile, within galaxies, close encounters between stars occasionally eject one or both participants. Though rare, given the enormous distances between stars, over cosmic timescales these events add up, gradually reducing galactic populations. Stars ejected with sufficient velocity might escape their galaxies entirely, joining the intergalactic diaspora of stellar wanderers. More dramatically, supermassive black holes at galactic centers occasionally consume nearby stars. Though these events are currently rare, over trillions of years, significant fractions of galactic populations may be devoured this way. The black holes grow larger, while their host galaxies diminish, a slow cosmic cannibalism that further contributes to the fading of galactic light. Even the stellar remnants themselves are not eternal. White dwarfs, though stable for trillions of years, eventually crystallize and cool to black dwarfs, invisible except through their gravitational influence. Neutron stars cool and dim, their lighthouse-like pulsations growing weaker until they become undetectable. Black holes maintain their gravitational grip, but emit almost no detectable radiation, their presence revealed only by their effect on nearby matter or through their exceedingly faint Hawking radiation. This Hawking radiation, a quantum effect predicted by Stephen Hawking in 1974, causes black holes to slowly evaporate over unimaginable timescales. A black hole with the mass of the Sunday would take approximately 10 to the 67 years to evaporate completely, far longer than the current age of the universe. More massive black holes last even longer, with supermassive black holes requiring up to 10 to the 100 years to dissolve. During this process, they emit faint radiation, growing hotter as they shrink, until exploding in a final burst of high-energy particles. This evaporation represents the final fading of galaxies, as even their densest remnants eventually dissolve into radiation. The process takes so long that the universe will have changed beyond recognition before it completes. The cosmic expansion will have carried all unbound matter beyond each other's event horizons, leaving isolated pockets of gravitationally bound systems surrounded by ever-expanding emptiness. Within these bound systems, predominantly the remnants of galaxy groups like our local group, matter gradually collapses towards central black holes. Stars, planets, gas, dust, all eventually fall into these cosmic devourers over timescales of tens to hundreds of trillions of years. The universe simplifies, with fewer but more massive black holes replacing the complex structures of earlier eras. These black holes then slowly evaporate through Hawking radiation, taking unimaginable amounts of time to dissolve completely. A black hole with the mass of the Milky Way's central supermassive black hole would require approximately 10 to the 100 years to evaporate, about 10 billion trillion times the current age of the universe. During this near-eternal process, the observable universe continues to contract as cosmic expansion accelerates. Eventually, even gravitationally bound systems like our local group will find themselves alone in an otherwise invisible cosmos, surrounded by regions beyond their event horizons. The universe fragments into isolated islands, each unaware of the others, each evolving independently toward its own heat death. For hypothetical observers in this distant future, the cosmos would appear radically different than it does today. No distant galaxies would be visible, their light unable to overcome cosmic expansion. No cosmic microwave background would be detectable, its photons stretched to wavelengths too long to register. No evidence would remain of the hot, dense early universe, of cosmic expansion, of the vast structures we observe today. This cosmic amnesia, this loss of evidence, represents another way in which the universe fades from view. Not only do objects grow distant or dim, but the clues that allow us to reconstruct cosmic history gradually disappear. The universe forgets itself, its past hidden by its own evolution. its history erased by time. Yet this fading is not uniform. As normal matter disappears into black holes, as black holes evaporate through Hawking radiation, the universe does not become structureless. Dark energy, that mysterious force driving cosmic acceleration, continues to influence cosmic evolution. Its density remains constant as space expands, making it increasingly dominant over matter, which thins as the volume it occupies grows. This growing dominance of dark energy ensures that the fading and vanishing of galaxies continues indefinitely. The observable universe constantly shrinks as more regions accelerate beyond our cosmic horizon. The expansion of space ensures that even if new structures somehow formed, they would quickly disappear from view, their light unable to reach distant observers. The fading of galaxies and vanishing of stars is not just a future phenomenon, but an ongoing process. It began with the first stellar deaths billions of years ago, and continues today as massive stars explode. As cosmic expansion carries distant galaxies beyond our horizon, as the rate of star formation gradually declines throughout the observable universe. We live in a transitional era, able to observe both the birth of new stars and the death of old ones, both nearby galaxies and extremely distant ones. We can see the cosmic microwave background, measure the expansion of space, detect the influence of dark energy. From these observations, we reconstruct cosmic history and project its future evolution, including the eventual fading of all galaxies and stars. But this window of observability is temporary. In the far future, much of the evidence we rely on will have disappeared. Distant galaxies will have accelerated beyond our horizon. The cosmic microwave background will be stretched to undetectable wavelengths. Star formation will have ceased, leaving only aging stellar populations and their remnants. The universe will appear smaller, simpler, less diverse, with fewer clues to its true nature and history. This eventual simplification represents the final sense in which galaxies fade from view. The universe not only grows darker and emptier, but also less complex, less structured, less informative. The rich tapestry of cosmic structure, built over billions of years from quantum fluctuations in the early universe, gradually unravels, leaving an increasingly uniform and featureless void. In time, the universe will shrink, not in space, but in sight. The question seems simple, almost childlike in its directness. Does the universe end somewhere? Is there an edge, a boundary, a final frontier beyond which nothing exists? This fundamental query has haunted human contemplation since we first gazed at the stars and wondered about our place in the cosmos. Yet the apparent simplicity of the question masks profound complexity. It forces us to confront not just the limits of our knowledge, but the limits of our conceptual frameworks, our language, our ability to comprehend reality at its most fundamental level. It challenges our intuitive notions of space and boundary, of inside and outside, of finite and infinite. Throughout history, humans have imagined the universe in terms drawn from everyday experience. Ancient cosmologies often envisioned the heavens as a dome or sphere surrounding a flat Earth, with some definite boundary separating the cosmic from the supercosmic. Medieval thinkers, following Aristotle, conceived of nested crystalline spheres carrying the planets and stars, with the outermost sphere marking the edge of creation. Even after Copernicus displaced Earth from the center, many still imagined some final sphere of fixed stars enclosing all of space. These models shared a common feature. They all proposed some boundary, some edge beyond which one could not travel. But they also raised a tantalizing question. What lies beyond this boundary? What exists outside the universe? The very question seems paradoxical, since the universe, by definition, encompasses everything that exists. If something exists beyond the boundary, then it too must be part of the universe, and the boundary must not have been the true edge after all. This paradox led thinkers like Lucretius in ancient Rome to propose an infinite universe with no boundary. If a boundary existed, he reasoned, one could throw a spear toward it. Either the spear continues past the boundary, in which case there must be space beyond, or something blocks the spear, in which case this blocking entity becomes the new boundary, and we can repeat the question. No finite boundary seems logically satisfactory. Modern cosmology approaches this question more mathematically, drawing on Einstein's general theory of relativity, our best description of gravity and space-time. This theory allows for different geometries of the universe as a whole, different ways that space can be curved or shaped. These geometries determine whether the universe is finite or infinite, bounded or unbounded, and what we might mean by an edge in a cosmic context. Three primary geometries emerge from general relativity, each with profound implications for our question. The universe could be positively curved like the surface of a sphere, negatively curved like a saddle, or flat like a plane. These refer not to the distribution of matter within the universe, but to the intrinsic geometry of space itself, the stage upon which cosmic drama unfolds. A positively curved universe, like a sphere, would be finite but unbounded. Just as the surface of a sphere has no edge yet contains a finite area, such a universe would contain a finite volume while having no boundary. An explorer could travel forever without encountering an edge, eventually returning to their starting point after circumnavigating the cosmic whole, just as a traveler on Earth can journey continuously eastward and ultimately return from the west. But this analogy has limitations. The surface of a sphere is two-dimensional, embedded in three-dimensional space. We can easily visualize it from the outside, seeing its curved nature. The universe, with its three spatial dimensions, cannot be visualized in the same way. We cannot step outside it to see its overall shape. Its curvature must be inferred from measurements made within, from the behavior of light rays and the trajectories of particles. A negatively curved universe would have a hyperbolic geometry, like a saddle shape extended in all directions. Such a universe would most likely be infinite, extending without limit. Parallel lines in such a space diverge, and the circumference of a circle grows more rapidly with radius than in flat space. An explorer could journey forever, without encountering a boundary or returning to their starting point. The universe would have no edge, no outside, just endless space expanding in all directions. A flat universe, the option most consistent with current observations, could be either finite or infinite. If flat and infinite, it would extend forever in all directions, with no boundary or edge, like an infinite plane. Parallel lines would remain parallel, never meeting or diverging. The geometry would be the familiar Euclidean space of high school mathematics, extended without limit in three dimensions. But a flat universe could also be finite if it has a non-trivial topology, a concept that extends beyond simple curvature to the overall connectedness of space. Imagine a flat sheet of paper. It represents infinite space. Now take that sheet and connect the left edge to the right, forming a cylinder. The space remains locally flat, but has become finite in one dimension. Connect the remaining edges, and you create a torus, or donut shape, finite in all dimensions, yet still locally flat. Similarly, our three-dimensional universe could be flat, yet finite, if it connects back on itself in certain ways. A cosmic traveler in such a universe would never encounter an edge or boundary, but might eventually return to their starting point, having circumnavigated the entire cosmos. The universe would appear to repeat, with identical copies of galaxies appearing at regular intervals in certain directions. Current observations strongly favor a flat or very nearly flat universe. Measurements of the cosmic microwave background, the afterglow of the Big Bang, show that light rays travel as they would in flat space, with triangles containing exactly 180 degrees and parallel lines maintaining constant separation. Any curvature must be extremely slight, with a radius far larger than our observable horizon. This flatness is thought to be a consequence of cosmic inflation, a period of exponential expansion in the first fraction of a second after the Big Bang. Inflation would have stretched any initial curvature to near flatness, just as inflating a balloon makes its surface appear increasingly flat to an ant crawling upon it. The larger the balloon, the flatter it seems locally, and our inflated universe appears extremely flat indeed. But these observations cannot definitively distinguish between a flat infinite universe and a flat finite one with large-scale connections. Both would appear identical within our observable bubble. To detect a finite topology, we would need to observe matching patterns of galaxies on opposite sides of the sky, a cosmic hall of mirrors, revealing the universe's connectedness. Current searches have found no compelling evidence for such repetition, suggesting that if the universe does connect back on itself, it does so on scales larger than we can currently observe. The distinction between finite and infinite, between bounded and unbounded, becomes even more complex when we consider the expansion of space. The universe expands not like an explosion into pre-existing space, but like a stretching of space itself. Galaxies do not move through static space but remain relatively stationary as the space between them increases. This expansion has profound implications for the question of cosmic edges. In an expanding universe, the concept of size becomes time-dependent. A finite universe grows larger with time. An infinite universe remains infinite, but becomes less dense as space stretches. The observable portion, limited by the speed of light and the age of the universe, also changes, encompassing different regions as time proceeds. Any discussion of cosmic boundaries must specify not just where, but when. The expansion of space also creates effective boundaries that, while not edges of the universe itself, function as limits to observation and interaction. The cosmic event horizon, beyond which events are forever hidden due to accelerating expansion, divides the universe into observable and unobservable regions. Light from beyond this horizon will never reach us, no matter how long we wait. This is not an edge in space, but in causal connection, a boundary between the knowable and the eternally unknown. These considerations reveal the inadequacy of our intuitive notions of boundary and edge when applied to the cosmos as a whole. In our everyday experience, a boundary divides one region from another, inside from outside, here from there. But the universe, by definition, encompasses everything that exists. There is no outside, no beyond, no larger container within which it sits. An edge, if it existed, would not separate the universe from something else, but would be a feature within the universe itself, a place where space simply ends. Can space simply end? Our intuition rebels against this notion, expecting some barrier, some wall or force that prevents further travel. But any such barrier would itself exist in space, would have location and extent, would be part of the universe rather than its edge. The concept of an absolute edge to space itself challenges not just our imagination, but our logical frameworks. Some theories in quantum gravity, attempts to reconcile general relativity with quantum mechanics, suggest that space may indeed be discrete at the smallest scales, composed of minimal units sometimes called spacetime atoms, or quanta. If true, this discreteness might provide a natural notion of boundary, a scale below which the concept of space itself breaks down. But this would be a limit in size, not in extent, a boundary of the very small, rather than the very large. Other theories propose extra dimensions beyond the three of space, and one of time that we directly experience. String theory, for example, suggests that our universe might be a three-dimensional brane, a kind of membrane, floating within a higher dimensional bulk. In this picture, what we perceive as our universe does have a boundary, but one that extends into dimensions we cannot directly observe or interact with. The edge exists, but not in a direction we can point to or travel toward. These theoretical speculations highlight the challenge of discussing cosmic boundaries in conventional terms. Our language and concepts evolved to describe middle-sized objects in terrestrial settings, strain when applied to the universe as a whole. We lack the intuitive frameworks to truly grasp what an edge to all of space might mean, or how infinite space might be structured. This conceptual vertigo intensifies when we consider the distinction between the observable universe and the universe as a whole. The observable universe, everything we can potentially see, is definitely finite, limited by the speed of light and the age of the cosmos. It forms a sphere around any observer with a current radius of about 46.5 billion light-years, accounting for cosmic expansion. This sphere has a boundary, the cosmic horizon, beyond which we cannot see. But this boundary is observational, not physical. It marks the limits of our cosmic vision, not the edge of space itself. Beyond this horizon, the universe continues, filled with galaxies and voids, stars and planets, all evolving according to the same physical laws that govern our observable region. At least, this is what the cosmological principle, the assumption that the universe is homogeneous and isotropic on the largest scales, would suggest. The actual universe, everything that exists, whether observable from our location or not, may be vastly larger than our observable bubble, perhaps even infinite. If infinite, it has no edge by definition, extending without bound in all directions. The observable portion would then be an infinitesimal fraction of the whole, like a single grain of sand on an endless beach. Even if the universe is finite, current estimates based on its observed flatness suggest it must be at least 250 times larger than our observable region. The cosmic horizon obscures most of what exists, limiting not just our observations but our knowledge. The question of whether the universe ends somewhere may have a definite answer, but one that lies beyond our current ability to determine empirically. This uncertainty reflects a fundamental limitation of cosmology as a science. Unlike laboratory physics, where experiments can be repeated under controlled conditions, cosmology deals with a single universe, a unique sample from which we must extract all our knowledge. We observe it from a specific location at a specific time, with all the biases and limitations that entails. Our theories must extrapolate from this limited perspective to the universe as a whole, a leap that inevitably involves assumptions and approximations. The cosmological principle, the assumption that the universe is roughly the same everywhere and in all directions on the largest scales, provides a foundation for this extrapolation. It suggests that what we observe locally reflects cosmic properties globally, that the physics we measure here applies everywhere. This principle has proven remarkably successful in explaining our observations, from the distribution of galaxies to the uniformity of the cosmic microwave background. But the principle remains an assumption, not a proven fact. It might break down beyond our observable horizon, or at scales so large that we cannot currently detect them. The universe might have regions with different properties, different physics, different evolutionary histories. It might be finite or infinite, connected in complex topological ways, or structured in dimensions beyond our direct perception. These possibilities are not merely philosophical, but emerge naturally from theories like cosmic inflation. Inflationary theory suggests that our observable universe expanded from a tiny quantum fluctuation, one of potentially countless such fluctuations occurring in a broader inflationary space. This eternal inflation would create a multiverse, an endless sea of bubble universes, each with its own laws and constants, its own evolutionary history. In such a multiverse, the question of whether the universe ends somewhere becomes even more complex. Each bubble universe might be finite or infinite, bounded or unbounded, depending on its specific properties. The multiverse as a whole might be infinite, extending without limit, while containing finite bubbles within it. The boundary between bubbles would not be an edge of all existence, but an interface between different cosmic regions, a transition rather than an absolute end. This perspective transforms our question from a cosmological one to a metaphysical one. It asks not just about the structure of physical space, but about the nature of reality itself, about how we define the universe, about the limits of knowledge and observation. It pushes at the boundaries not just of science, but of philosophy, of language, of human comprehension. Yet despite these profound challenges, we continue to explore the question, to observe, to theorize, to imagine. We develop mathematical models that extend beyond what we can see, guided by the patterns we observe within our horizon. We test these models against new observations, refining our understanding of the cosmos step by step. We push our instruments to their limits, squeezing every bit of information from the light that reaches Earth. Current observations suggest several possibilities for the global structure of the universe. It might be infinite and flat, extending without bound in all directions, with no edge or boundary. It might be finite but unbounded, like a higher dimensional analog of a sphere, allowing travel in any direction without encountering an edge, yet containing only a finite volume. It might be finite and connected in complex ways, like a cosmic version of a torus or more exotic shape, creating a kind of hall of mirrors where traveling far enough in certain directions would return you to your starting point. These possibilities differ in their mathematical properties, in their implications for cosmic evolution, in their philosophical ramifications, but they share a common feature. None involves an absolute edge, a boundary where space simply stops, with nothing beyond. Such an edge seems not just difficult to imagine, but logically problematic, raising the paradox that troubled Lucretius 2,000 years ago. If space ends, what lies beyond the endpoint? And if something lies beyond, how can the endpoint be the true edge of everything? Some theorists have proposed cosmic strings, domain walls, or other topological defects that might mark boundaries between different regions of the universe, perhaps with different physical properties. These would not be edges of all space, but transitions between different cosmic domains, interfaces, rather than absolute ends. They would exist within the broader cosmos, features of its structure, rather than limits to its extent. Other theories suggest that the universe might be a kind of simulation, a constructed reality with built-in boundaries or constraints. In this scenario, an edge might exist not in physical space, but in the underlying computational substrate, a limit to the simulation's resolution or extent. This speculative idea, while not currently testable, highlights how the concept of a cosmic boundary depends on our most fundamental assumptions about the nature of reality. The search for cosmic edges also extends to time. Does the universe have a beginning or an end temporally, a first or last moment? The Big Bang, often misunderstood as an explosion in pre-existing space, marks the earliest moment we can currently describe with our physics. Before this, our theories break down, unable to cope with the extreme conditions of infinite density and temperature, suggested by extrapolating cosmic expansion backward without limit. Some theories propose that the Big Bang was not the absolute beginning, but a transition from an earlier state, perhaps a previous contracting phase, a quantum fluctuation from nothing, or an inflation from a pre-existing space. Similarly, the ultimate fate of the universe, whether it expands forever, recollapses, or undergoes some more exotic transition, remains an open question, dependent on the properties of dark energy and the overall geometry of space. These temporal boundaries, the beginning and end of cosmic time, connect intimately with the question of spatial boundaries. In some models, like a closed universe that expands and then recontracts, space has no edge, but time has both a beginning and an end. In others, like an eternally inflating multiverse, both space and time might extend infinitely, with neither beginning nor end on the largest scales, though individual regions might have finite histories. The intertwining of space and time in Einstein's relativity further complicates our question. Space and time are not separate entities but aspects of a unified spacetime, curved by matter and energy, warped by gravity. The edge of the universe, if it exists, would be a feature of this four-dimensional spacetime, not just of three-dimensional space at a particular moment. It might involve both when and where, location and duration, inseparably linked. This complexity reveals why the seemingly simple question, does the universe end somewhere, resists a simple answer. It depends on what we mean by universe, by end, by somewhere. It involves not just the physical structure of space, but the nature of observation, the limits of knowledge, the foundations of reality itself. It pushes us to the borders, not just of the cosmos, but of comprehension. Yet this very difficulty makes the question valuable. It forces us to examine our assumptions, to clarify our concepts, to stretch our imagination beyond everyday experience. It reminds us that the universe is not just what we see, but what exists, whether visible to us or not. It humbles us with the vastness of the cosmos and the limitations of our knowledge. It inspires us to continue observing, theorizing, questioning. Current evidence, particularly the observed flatness of space and the uniform distribution of matter on the largest scales, favors a universe that is infinite, or at least much larger than what we can observe. The apparent edge of our cosmic vision, the horizon beyond which we cannot see, is not the edge of the universe itself, but a limit to our perspective, a boundary of observation rather than its. The cosmos continues beyond, perhaps without end, filled with galaxies and voids similar to those we observe nearby. But this conclusion remains tentative, based on extrapolation from limited evidence, dependent on assumptions that might not hold universally. The universe might yet surprise us, revealing structures or properties beyond our current models, challenging our most fundamental assumptions about cosmic architecture. The edge we seek, the boundary between existence and non-existence, may not be a place at all but a concept, a limit to our understanding, rather than a feature of reality. The universe might be edgeless, not because it extends infinitely, but because the very notion of an absolute boundary makes no sense in the context of all that exists. There cannot be an outside to everything, a beyond to the totality. Some edges are not walls, they are mirrors, bending space around itself. The universe might connect back upon itself, creating not a boundary, but a continuity, a seamless whole that is both finite and unbounded. Like the surface of a sphere, which has no edge yet contains only a finite area, the cosmos might curve back upon itself in higher dimensions, allowing limitless travel without encountering an absolute end. This topological complexity offers a resolution to the paradox that troubled ancient thinkers. The universe can be finite without having an edge, bounded without a boundary in the conventional sense. It can contain all that exists without needing an absolute limit, a final frontier beyond which lies nothing. The edge dissolves into connection, the boundary into continuity. Yet even this elegant solution raises further questions. If the universe curves back upon itself, what determines its size and shape? Why this particular geometry rather than another? What physical process set these parameters in the earliest moments of cosmic history? The answer may lie in quantum fluctuations during cosmic inflation, in the interface between quantum mechanics and gravity, in realms where our current theories reach their limits. As we contemplate these profound puzzles, we must remember that our questions about cosmic boundaries are shaped by our human perspective, our evolution as middle-sized creatures on a small planet orbiting an ordinary star. Our intuitions about space and boundary, inside and outside, finite and infinite, emerge from our specific evolutionary history. Our particular sensory apparatus, our unique cognitive architecture. The universe itself is under no obligation to conform to these intuitions. It may be structured in ways that we struggle to visualize or articulate, that challenge our conventional categories and concepts. The edge we seek may not exist in any form we can easily imagine, or may exist in a form so alien to our everyday experience that we lack the conceptual frameworks to truly grasp it. This possibility does not render our question meaningless, but enriches it, transforming it from a simple query about cosmic geography to a profound exploration of the limits of human understanding. It reminds us that the universe is not just what we can observe or comprehend, but what exists, whether accessible to our minds or not. The silent border of the cosmos may not be a wall or a barrier, a place where space ends and nothingness begins. It may be a fold, a connection, a continuity that transforms our notion of boundary itself. The edge we perceive may be an artifact of our limited perspective, a horizon rather than a limit, a threshold of visibility rather than a border of existence. Some edges are not walls, they are mirrors, bending space around itself. As we approach the silent border of the cosmos, the question naturally arises, could there be something beyond? Not just more of the same universe, extending perhaps infinitely, but something fundamentally different, a reality separated from our own by some boundary or threshold. This question pushes us beyond observational astronomy into the realm of theoretical physics and even metaphysics, challenging our most basic assumptions about the nature of reality. The concept of beyond itself becomes complex when applied to the cosmos as a whole. In everyday experience, beyond implies direction, a path that can be followed, a distance that can be traversed. But if the universe encompasses all of space and time, all matter and energy, what could it mean for something to exist beyond it? Where would this beyond be located? and how would it relate to our reality? Modern theoretical physics offers several frameworks for thinking about this question, ways of conceptualizing a beyond that does not require an outside to everything. These theories emerge not from idle speculation, but from attempts to resolve contradictions in our current understanding, to unify quantum mechanics and general relativity, to explain observations that challenge conventional models. They suggest that reality may be larger, more complex, and more diverse than we previously imagined. The first framework comes from inflationary cosmology, the theory that the universe underwent a period of exponential expansion in its first fraction of a second. This inflation, driven by a quantum field called the inflaton, stretched a microscopic region of space to macroscopic size, creating our observable universe. But inflation might not have ended everywhere simultaneously. In some regions, it continues, eternally creating new expanding bubbles, each a universe unto itself. This scenario, known as eternal inflation, gives rise to a multiverse, an endless sea of bubble universes, embedded within an ever-inflating background. Each bubble universe emerges from a quantum fluctuation, a random variation in the inflaton field that triggers a transition from inflationary expansion to the slower expansion we observe today. These bubbles expand, potentially becoming infinite in their own right, separated from each other by regions still undergoing inflationary expansion. In this picture, the beyond exists as other bubble universes, regions that began like our own but evolved separately, with potentially different physical properties. These bubbles might have different distributions of matter, different constants of nature, different numbers of spatial dimensions. They would be, in effect, other universes, each with its own physics, its own evolutionary history, its own possibilities. These bubble universes would be causally disconnected from our own, separated by distances expanding faster than light can travel. No signal could cross from one bubble to another. No information could be exchanged. No interaction could occur once the bubbles formed. They would exist beyond our universe, not in a spatial direction we could point to, but in a deeper sense, as regions fundamentally isolated from our own by the dynamics of cosmic inflation. The eternal inflation scenario emerges naturally from combining quantum field theory with general relativity, from understanding how quantum fluctuations would behave in an exponentially expanding spacetime. It is not an ad hoc addition to cosmology, but a consequence of physics we already understand, extended to the earliest moments of cosmic history. While not definitively proven, it offers a compelling explanation for the flatness, homogeneity, and isotropy of our observable universe. A second framework for thinking about beyond comes from string theory, our most developed attempt to unify all fundamental forces into a single theoretical framework. String theory suggests that the basic constituents of reality are not point-like particles but tiny vibrating strings, whose different modes of vibration manifest as different particles and forces. These strings exist not just in the three spatial dimensions we directly experience, but in additional, compact dimensions, curled up so tightly that we cannot perceive them. In some versions of string theory, our universe is conceptualized as a brane, a membrane-like structure extending through three spatial dimensions, floating within a higher dimensional bulk space. Other branes might exist within this bulk, other universes with their own three-dimensional spaces, their own matter and energy, their own physics. These branes would be beyond our universe, not in a direction within our three dimensions, but in the extra dimensions of the bulk space. This brane multiverse differs from the inflationary multiverse in crucial ways. The bubble universes of eternal inflation share a common origin and initial conditions, diverging through quantum fluctuations in the inflaton field. Brane universes might have entirely different origins, existing independently within the higher dimensional bulk, perhaps even interacting through gravitational effects that propagate through the extra dimensions. Such interactions could potentially leave observable traces. If another brane passed close to ours in the bulk space, the gravitational attraction might create ripples or distortions in our spacetime, perhaps detectable through careful measurements of the cosmic microwave background or gravitational wave observatories. These would be echoes from beyond, signals not from distant regions of our universe, but from a separate, cosmic reality. A third framework comes from quantum mechanics itself, specifically the many worlds interpretation proposed by Hugh Everett in 1957. This interpretation suggests that quantum events do not have single, definite outcomes, but create branching realities, parallel universes that include all possible outcomes. When a quantum particle is measured, the universe splits into multiple versions, one for each possible measurement result, with observers in each branch experiencing only their own version of reality. In this picture, the beyond exists as parallel quantum realities, universes identical to our own, up to the point of a quantum decision, then diverging along different paths. These parallel worlds would not exist in spatial dimensions beyond our own, but in a more abstract sense, as alternate realities within the mathematical structure of the quantum wave function. They would be beyond our reach not because of spatial separation, but because of the nature of quantum decoherence, which prevents interference between macroscopically distinct quantum states. The many worlds interpretation remains controversial among physicists, with ongoing debates about its ontological implications, its relationship to probability, and whether it truly resolves the measurement problem in quantum mechanics. Yet, it offers a logically consistent way of understanding quantum phenomena without invoking consciousness or non-local effects, and its implications for a multiverse of parallel realities emerge directly from the mathematics of quantum theory. These three frameworks, eternal inflation, string theory brains, and quantum many worlds, offer different ways of conceptualizing what might exist beyond our observable universe. They are not mutually exclusive. Each might be true in its own way, describing different aspects of a reality more complex than any single theory captures. Together, they suggest that the beyond is not a single concept, but a constellation of possibilities, a multifaceted transcendence of our conventional cosmic understanding. But these theoretical frameworks, while grounded in mathematics and physical principles, remain speculative. They extend beyond what we can currently observe or test directly, pushing the boundaries of what qualifies as scientific knowledge. How seriously should we take them? Are they genuine possibilities for what might exist beyond our cosmic horizon, or merely mathematical constructs without physical reality? The answer depends partly on philosophical perspectives on the nature of scientific theories. Some philosophers of science, following an instrumentalist approach, would argue that theories are merely tools for predicting observations, not descriptions of an underlying reality. In this view, talk of multiverses, or extra dimensions, is meaningful only to the extent that it generates testable predictions about our observable world. Others, adopting a realist stance, would contend that successful scientific theories capture something genuine about reality, even if that reality extends beyond our direct observation. The predictive success of quantum mechanics and general relativity, despite their counterintuitive implications, suggests that mathematical consistency and explanatory power provide reasons to take seriously even those aspects of theories that transcend current empirical access. A middle path, sometimes called inference to the best explanation, suggests that we should provisionally accept theories that provide the most coherent, comprehensive, and simple explanation of observed phenomena, even if parts of these theories refer to unobservable entities or processes. By this standard, multiverse theories deserve consideration insofar as they naturally explain features of our observable universe that otherwise seem improbable or fine-tuned. The fine-tuning of physical constants provides a concrete example. The fundamental constants of nature, such as the strength of gravity, the mass of the electron, and the energy of the vacuum, appear exquisitely calibrated to allow the formation of complex structures like galaxies, stars, and life. Small changes in these values would create a universe inhospitable to complexity, either collapsing immediately or expanding so rapidly that no structures could form. This apparent fine-tuning admits several explanations. It might reflect design by an intelligence, a cosmic coincidence of astronomically low probability, or a necessary consequence of undiscovered physical principles. But it might also indicate a vast multiverse with varying physical constants, in which we necessarily find ourselves in a region where the constants allow our existence. This last explanation, known as the anthropic principle, becomes more compelling if multiverse theories independently emerge from our best physical theories. While we cannot directly observe other universes, we might find indirect evidence for their existence through anomalies or patterns in our observable cosmos. The CMB cold spot, an unusually large cold region in the cosmic microwave background, has been proposed as a possible imprint from a collision with another bubble universe. Unexplained alignments or correlations in large-scale cosmic structures might hint at influences from beyond our observable horizon. Precise measurements of dark energy might reveal subtle variations consistent with a landscape of possible vacuum energies, as suggested by string theory. These potential signatures remain tentative and controversial, with conventional explanations still viable for most anomalies. But they illustrate how the beyond might leave traces within our observable universe, how the boundaries between the seen and the unseen might be less absolute than they initially appear. They suggest that while other universes may be separated from ours by vast distances, extra dimensions, or quantum decoherence, they need not be completely invisible to careful cosmic detective work. The search for such signatures represents a fundamental shift in cosmology. From studying the universe we can see to inferring the larger reality in which it is embedded. It pushes the boundaries of scientific method, requiring new statistical techniques, new theoretical frameworks, new ways of connecting observation with theory. It asks not just what exists within our cosmic horizon, but what must exist beyond it, to explain what we observe within. This search also raises philosophical questions about the limits of knowledge, the nature of evidence, the relationship between mathematics and physical reality. Can we claim to know what exists beyond our observable universe? What standard of evidence applies to regions permanently hidden from direct observation? Does the mathematical consistency and explanatory power of a theory provide sufficient reason to accept its implications for unobservable domains? These questions have no simple answers, reflecting deep issues in the philosophy of science and the nature of scientific knowledge. They remind us that the beyond is not just a physical concept, but an epistemological one, a challenge to our understanding of what it means to know, to explain, to comprehend reality in its fullest sense. Yet despite these complexities, the possibility of something beyond our observable universe remains a compelling focus for theoretical physics and cosmology. It emerges naturally from our most successful theories, offers potential explanations for puzzling observations, and connects to fundamental questions about the nature of reality, the origin of physical laws, and our place in the cosmos. The multiverse concept, in its various forms, also transforms our understanding of cosmic uniqueness. If our universe is the only one, its specific properties acquire a special significance, demanding explanation in terms of necessity or purpose. But if our universe is one among many, its properties might reflect selection effects rather than fundamental necessity. We observe these specific physical constants because they allow our existence, not because they are the only possible values. This perspective shifts attention from the values of physical constants to the mechanisms that generate variation in these values across different cosmic domains. Instead of asking why the cosmological constant has its specific value, we ask what processes create a landscape of possible vacuum energies, and how regions transition between different energy states. The question becomes less, why these specific laws, and more, what meta-laws govern the variation of laws across the multiverse. This approach has drawn criticism from some physicists who argue that multiverse theories, by explaining everything, explain nothing. If all possible combinations of physical parameters exist somewhere in the multiverse, then any observation becomes consistent with the theory, robbing it of predictive power. Why strive to explain the specific features of our universe if they are merely a random selection from a vast landscape of possibilities? Proponents counter that multiverse theories do not abandon explanation, but shift it to a different level. They explain why our universe has life-permitting parameters, not by showing these parameters are necessary, but by demonstrating that they fall within the narrow range compatible with observers like ourselves. They transform apparent fine-tuning from a coincidence requiring explanation to an expected consequence of observer selection within a diverse cosmic reality. Moreover, Specific multiverse theories make distinct predictions about the distribution of parameters we should observe. If our universe is typical among those that contain observers, we should find ourselves not in a perfectly optimized environment, but in one that is minimally sufficient for our existence. The cosmological constant, for example, should be small enough to allow galaxy formation, but not dramatically smaller than necessary, a prediction consistent with its observed value. These predictions connect the beyond to the observable, providing potential tests for multiverse theories, despite their transcendence of direct observation. They illustrate how speculation about what exists beyond our cosmic horizon need not be metaphysical in a pejorative sense, but can generate empirical consequences, can be constrained by observation, can function as scientific hypotheses, rather than mere philosophical musings. The theoretical frameworks that suggest a beyond, a multiverse, a transcendence of our observable cosmos, themselves emerged from attempts to solve specific problems in physics and cosmology. Inflation was proposed to explain the flatness problem, the horizon problem, and the monopole problem in standard Big Bang cosmology. String theory developed as an approach to quantum gravity and the unification of fundamental forces. The many worlds interpretation addressed the measurement problem in quantum mechanics. These theories were not invented to create a multiverse, but led to multiverse implications through their internal logic and mathematical structure. The beyond emerged not from a desire to transcend our cosmic limits, but from following where our best physical theories led, from taking seriously their implications, even when these extended beyond our observational reach. This grounding in physics rather than metaphysics distinguishes modern multiverse theories from earlier speculations about other worlds or realities. They are not primarily philosophical or religious concepts, but scientific hypotheses, mathematical models with precise implications, theoretical frameworks capable of empirical engagement, even if indirect. They represent not a retreat from scientific methodology, but its extension into domains once considered beyond its reach. Yet the beyond suggested by these theories differs fundamentally from conventional notions of faraway places. It is not merely distant in space or time, but separated more profoundly by dimensional gaps, by causal disconnection, by quantum decoherence. It exists not in a direction we could point to or a place we could eventually reach, but in a deeper sense, as reality that transcends our cosmic bubble in ways that challenge our spatial and temporal intuitions. This transcendence connects scientific speculation about the beyond with philosophical and religious traditions that have long pondered realms beyond ordinary experience. The multiverse concept resonates with ancient notions of multiple worlds or planes of existence, from Hindu cosmology with its countless universes to medieval speculations about other worlds beyond our own. It gives scientific form to the intuition that reality might be larger, more diverse, more encompassing than what we directly observe. But there are crucial differences between scientific multiverses and their philosophical precursors. Modern multiverse theories emerge from specific mathematical models, make precise predictions about the properties of different cosmic domains, and connect to observable physics in our universe. They are not postulated as acts of cosmic imagination, but derive from mathematical consistency and physical principles, from following the logic of our best theories to their fullest implications. This grounding in physics provides constraints on speculation about the beyond. Not anything goes. Not every imaginable reality finds a place in scientific multiverse theories. The different cosmic domains must conform to the meta-laws that generate variation, must emerge from processes like eternal inflation, or quantum branching, or brain dynamics, must connect to our domain through logical and causal structures specified by the theories themselves. The beyond is not arbitrary, but ordered, not chaotic, but lawful, not disconnected from our reality, but related to it through precise mathematical relationships. This lawfulness of the beyond, this connection to our reality through mathematical structure, suggests that the transcendence of our cosmic limits need not imply an abandonment of understanding. The beyond may exceed our direct observation, may challenge our conventional categories, may push the boundaries of what we can visualize or articulate. But it remains, in principle, comprehensible through the language of mathematics, accessible to theoretical investigation, subject to indirect empirical constraints. The idea that reality might be larger, more complex, more diverse than what we directly observe is not new. Throughout history, humans have discovered that the world extends beyond their immediate experience, that there are realms and entities inaccessible to unaided perception, but nevertheless real and important. Microbes too small to see, galaxies too distant to visit, electromagnetic wavelengths outside our visual range, all became part of our understanding through instruments and theories that extended our perceptual and conceptual reach. The multiverse represents a continuation of this pattern, a further extension of reality beyond direct observation, a new horizon for human comprehension. Like earlier extensions, it emerges not from pure speculation, but from attempts to explain what we do observe, to resolve contradictions in our current understanding, to follow the internal logic of successful theories. And like earlier extensions, it challenges us to expand our conceptual frameworks, to develop new ways of thinking about reality, to embrace a cosmos larger and more complex than our ancestors imagined. This expansion of cosmic vision need not diminish human significance, but can enhance it. We become not merely inhabitants of a single universe, but participants in a reality that transcends our cosmic bubble. Contemplators of a multiverse we cannot directly observe, but can comprehend through mathematics and theory. Our consciousness reaches beyond our perceptual limits. Our minds grasp realities our senses cannot access. Our understanding extends to domains permanently hidden from direct observation. The silent border of the cosmos, in this perspective, is not the edge of all that exists, but a horizon of observation, a limit to what we can see rather than what is. Beyond this border, reality continues, perhaps in forms radically different from our observable domain, perhaps with different physical laws, different constants, different dimensions, different possibilities. These domains exist not in a place we could eventually reach, but in a sense more profound, as regions fundamentally separated from our own by the structure of reality itself. Yet this separation need not be absolute. Traces of the beyond might appear within our observable universe, subtle signatures of a larger reality imprinted on the cosmos we can see. The cold spot in the cosmic microwave background, unexplained alignments in large-scale structure, the specific values of physical constants. These might be whispers from beyond, hints of cosmic domains outside our observational reach. They remind us that the border between the seen and the unseen, while real, need not be impermeable to careful theoretical investigation. The multiverse concept also transforms our understanding of possibility and actuality. In traditional cosmology, what actually exists is a tiny subset of what could possibly exist, a single realization from a vast space of potential universes. But in a multiverse, many or all of these possibilities are realized somewhere, in some cosmic domain. Possibility and actuality blur, with the space of physical possibility largely or completely filled by actual cosmic regions. This perspective shifts our understanding of why our universe has its specific properties. Instead of seeking a unique explanation for why these precise physical parameters exist, we ask what processes generate a diversity of parameters across different cosmic domains, and why we find ourselves in a domain with these specific values. The explanation combines the mechanisms of multiverse generation with observer selection effects, with the fact that we necessarily exist in a region compatible with our own evolution, beyond the silence, beyond the darkness, beyond the edge of observation. What might exist there? More universes, perhaps, with their own galaxies and stars, their own planets, and possibly life, their own observers, gazing outward at their own cosmic horizons. Or, more exotic possibilities, realms with different dimensions, different physical laws, different concepts of space and time. Or deeper structures, fundamental realities from which our universe emerges as a particular expression, a specific manifestation of more abstract principles. These possibilities remain speculative, extending beyond what we can currently observe or test directly. But they emerge not from arbitrary imagination, but from the internal logic of our best physical theories, from attempts to resolve contradictions in our current understanding, from following the mathematics where it leads. They represent not an abandonment of scientific rigor, but its application to domains that transcend direct observation, guided by the principle that mathematical consistency and explanatory power provide clues to the nature of reality even beyond our cosmic horizon. The question of what exists beyond our observable universe thus connects to the deepest issues in physics and cosmology, to the unification of quantum mechanics and general relativity, to the origin of physical laws, to the nature of space and time themselves. It pushes the boundaries not just of what we know, but of how we know, challenging us to develop new methodologies, new standards of evidence, new ways of connecting theory with observation. Beyond the silence, perhaps more silence, or something new. Knowledge has horizons just as space does. There are limits not just to what we currently know, but to what we can know, boundaries beyond which observation and measurement become fundamentally impossible. These epistemic horizons shape our understanding of the cosmos, defining the border between the knowable and the unknowable, the boundary where science meets mystery. The most obvious constraint on cosmic knowledge is observational. We cannot see beyond our particle horizon, the maximum distance from which light could have reached us since the beginning of the universe. Given the finite age of the cosmos, approximately 13.8 billion years, and the finite speed of light, regions sufficiently distant have not had time to send signals that have yet arrived at Earth. They exist, presumably with galaxies and stars similar to those we observe nearby, but remain invisible to our telescopes. Their light still en route, their stories untold. This observational horizon expands with time as the universe ages, bringing previously invisible regions into view. With each passing second, photons from slightly more distant sources complete their journey to Earth, revealing galaxies and structures previously hidden. Given enough time, these regions would become visible, their light finally arriving after billions of years of transit through expanding space. But cosmic expansion creates a second, more profound constraint. Regions beyond our event horizon, approximately 16 billion light-years in the current era, recede faster than light due to the stretching of space itself. Light emitted from these regions, even if traveling at its maximum cosmic speed, fights a losing battle against an expansion that carries the source away faster than the signal can approach. These regions are not just currently invisible, but permanently so, forever beyond our observational reach, no matter how long we wait or how sensitive our instruments become. This event horizon represents a fundamental limit to knowledge, a boundary beyond which events cannot affect us, and therefore cannot be observed, measured, or known directly. What happens in these regions remains forever hidden, their reality inaccessible to empirical investigation from our cosmic vantage point. We can speculate, extrapolate, theorize about what exists beyond this horizon, but we cannot know, in the observational sense. That forms the foundation of empirical science. Yet even within our observable bubble, constraints on knowledge emerge from the nature of light and its interaction with matter. The cosmic microwave background, the oldest light we can detect with conventional telescopes, comes from when the universe was just 380,000 years old. Before this time, the cosmos was opaque, filled with a hot, dense plasma that scattered photons before they could travel far. This opacity creates a visual wall, a boundary beyond which electromagnetic observation cannot penetrate. Other messengers, like neutrinos and gravitational waves, can carry information from earlier cosmic epochs. Neutrinos decoupled from the primordial plasma when the universe was just 1 second old, while gravitational waves could potentially bear witness to the inflationary period in the first fraction of a second after the Big Bang. These alternative signals push our observational horizon earlier, but not to the very beginning. The Planck epoch, the first 10 to the negative 43 seconds, remains hidden behind a veil of quantum gravity, a domain where our current theories break down completely. These observational limits, set by the speed of light, cosmic expansion, and the opacity of the early universe, constrain what we can know through direct measurement. But theoretical limits on knowledge run deeper still, emerging from the fundamental nature of reality as described by our most successful physical theories, quantum mechanics and general relativity. Quantum mechanics introduces uncertainty at the most fundamental level, a fuzziness not due to practical limitations of measurement, but to the probabilistic nature of reality itself. The Heisenberg uncertainty principle states that certain pairs of properties, like position and momentum, cannot both be precisely determined simultaneously. The more accurately we measure one, the less accurately we can know the other. This is not a limitation of our instruments, but a fundamental feature of quantum systems, a limit to what can be known even in principle. This quantum uncertainty extends beyond individual particles to the vacuum itself. Quantum field theory reveals that empty space continuously fluctuates at the smallest scales, with particles and antiparticles briefly popping into existence before annihilating each other. These vacuum fluctuations generate a fundamental noise, a cosmic static that places limits on the precision of any measurement. No matter how sensitive our instruments, this quantum noise creates an irreducible uncertainty in our observations. General relativity, our best theory of gravity and space-time, introduces its own constraints on knowledge through the existence of black holes. Once matter crosses a black hole's event horizon, information about its state becomes permanently hidden from external observers. Light cannot escape, signals cannot be transmitted. The details of what happens inside remain forever concealed. This information loss challenges our understanding of fundamental physics, creating tensions with quantum mechanics, which suggests that information should always be preserved. The combination of quantum mechanics and general relativity creates even more profound challenges at the Planck scale, approximately 10 to the negative 35 meters, where space-time itself may become granular, probabilistic, fundamentally uncertain. At this scale, our current theories break down, unable to reconcile the quantum nature of matter with the geometric nature of gravity. What happens at the Planck scale? How space and time themselves behave? What fundamental principles govern reality at its most basic level? These questions push beyond what we currently know, or perhaps can know, without radical theoretical advances. These physical limits to knowledge are compounded by cognitive ones. Our minds evolved to navigate the middle world of medium-sized objects, moving at moderate speeds, not to intuitively grasp quantum superposition or curved spacetime. We rely on mathematics to extend our cognitive reach, to describe realms beyond direct sensory experience, to formulate theories that transcend our intuitive frameworks. But even mathematics has its limits, with theorems like Gödel's incompleteness, showing that any consistent formal system sufficiently complex to include arithmetic must contain truths that cannot be proven within that system. Together, these observational, theoretical, and cognitive constraints create horizons of knowledge, boundaries beyond which certainty gives way to speculation, measurement to modeling, knowing to wondering. They define the edge of what we can know, the silent border where science meets mystery, where the observable fades into the unobservable, where theory reaches the limits of empirical verification. Yet these horizons are not static, but dynamic, shifting with advances in technology, theory, and methodology. Instruments like the James Webb Space Telescope push the boundaries of the observable, revealing galaxies from when the universe was less than 5% of its current age. Theoretical frameworks like string theory and loop quantum gravity attempt to transcend the limits of our current understanding, to peer beyond the Planck scale into the quantum nature of space-time itself. Computational tools like simulations and machine learning extend our cognitive capabilities, allowing us to model and visualize phenomena beyond direct human comprehension. These advances continually reshape the border between the known and the unknown, pushing it outward in some directions while revealing new depths of mystery in others. They transform what was once unknowable into the merely unknown, what was once unimaginable into the theoretically described. But they also reveal new horizons, new limits, new boundaries to knowledge that replace those they transcend. Consider dark matter and dark energy, which together constitute about 95% of the energy content of the universe. We infer their existence from their gravitational effects, from the rotation curves of galaxies, from the expansion rate of the cosmos. But their fundamental nature remains unknown, their properties largely unconstrained, their relationship to the standard model of particle physics unclear. They represent known unknowns, phenomena whose existence we have established but whose essence remains beyond our current understanding. Or consider the early universe, the first fraction of a second after the Big Bang, when conditions were so extreme that our current theories cannot fully describe them. We can extrapolate backward using general relativity and quantum field theory to model earlier and earlier epochs. But at some point, around the Planck time, these theories break down, unable to handle the extreme densities and temperatures that prevailed. What happened during this earliest moment? How space and time themselves emerged? These questions lie at the edge of what we can currently know. Even more profound is the question of why there is something rather than nothing. Why the universe exists at all. Science can describe how the cosmos evolved from an initial hot, dense state, how galaxies formed from primordial fluctuations, how elements were forged in stellar furnaces, how planets condensed from disks of gas and dust around young stars. But the ultimate origin, the reason for existence itself, may lie beyond what science can address, a question that transcends empirical investigation. These limits to knowledge might seem discouraging, suggesting that complete understanding of the cosmos lies forever beyond our reach. But they can also be seen as invitations to intellectual humility, to an appreciation of mystery, to a recognition that reality may be richer, deeper, more complex than our theories can fully capture. They remind us that knowledge is a journey, not a destination, a continual process of discovery, rather than a final state of complete understanding. The horizons of knowledge also inspire creative theoretical work, pushing scientists to develop new frameworks, new methodologies, new ways of connecting theory with observation. String theory, loop quantum gravity, inflationary cosmology, these attempts to peer beyond our current understanding draw their motivation partly from the desire to transcend existing limits, to push the boundaries of the knowable, to expand our cosmic vision beyond its present horizons. But these theoretical efforts face a fundamental challenge. How do we test theories that address domains beyond direct observation? How do we distinguish between competing models when their differences manifest only in regimes we cannot directly probe? How do we avoid the trap of unfalsifiable speculation while still pushing the boundaries of scientific understanding? The answer lies partly in indirect testing, in finding observable consequences of theories that address unobservable domains. Inflation, though it occurred long before we could directly observe the universe, leaves traces in the cosmic microwave background, in the distribution of galaxies, in the large-scale structure of the cosmos. String theory, though it operates at scales far smaller than we can directly probe, might predict specific patterns of supersymmetric particles detectable at particle accelerators, or distinctive signatures in primordial gravitational waves. These indirect tests provide a bridge between the observable and the unobservable, allowing theories that transcend our observational horizons to maintain contact with empirical reality. They ensure that speculation remains grounded, that theories addressing unknowable domains still connect to knowable ones, that the expansion of our theoretical understanding remains guided by the constraint of observable fact. Another approach involves theoretical parsimony, the principle that, all else being equal, simpler explanations should be preferred over more complex ones. When direct observation is impossible, theories that introduce fewer new entities, assumptions, or principles may have an advantage. This principle, often called Occam's razor, serves as a guide when empirical evidence alone cannot distinguish between competing models of unobservable domains. But theoretical parsimony must be balanced against explanatory power, the ability of a theory to account for observed phenomena and make successful predictions. A simpler theory that fails to explain key observations is not preferable to a more complex one that succeeds. The challenge lies in finding the optimal balance, the theory that explains the most with the least, that accounts for the observable while making the most modest claims about the unobservable. These methodological principles, indirect testing and theoretical parsimony balanced against explanatory power, provide guidance for navigating the edge of what we can know. They allow science to extend its reach beyond direct observation without sacrificing its empirical foundation, to speculate about unobservable domains while maintaining connection to observable reality, to push the boundaries of knowledge while acknowledging its limits. Yet, even with these principles, certain questions may remain permanently beyond scientific resolution. Is it meaningful to ask about what existed before the Big Bang, if time itself began with this cosmic origin? Can we determine whether the universe is actually infinite or only potentially so, given our finite observational horizon? How do we evaluate competing interpretations of quantum mechanics that make identical empirical predictions but propose radically different underlying realities? These questions push at the boundaries not just of what we know, but of what counts as scientific knowledge, of what questions science is equipped to answer, of where the border lies between physics and metaphysics. They remind us that science, powerful as it is, represents just one approach to understanding reality, one lens through which to view the cosmos, one mode of inquiry among many. The recognition of limits to scientific knowledge need not imply a retreat to irrationality or a surrender to mysticism. It simply acknowledges the scope and boundaries of a particular method of investigation, the domain within which empirical testing and mathematical modeling can effectively operate. Beyond these boundaries, other modes of inquiry, from philosophy to art to spiritual contemplation, may offer complementary perspectives, different ways of engaging with the mysteries that transcend scientific resolution. This multifaceted approach to understanding seems particularly appropriate when considering the edge of the observable universe, the silent border where light fails and observation becomes impossible. This border marks not just a limit to what we can see, but a challenge to how we know, a threshold where our conventional methods of investigation reach their limits and must be supplemented by theoretical extrapolation, mathematical modeling, perhaps even philosophical reflection. The cosmos does not owe us an answer. It exists independent of our observation, our theories, our need for explanation. The universe is under no obligation to be comprehensible to human minds, to fit neatly within our conceptual frameworks, to resolve all its mysteries for our intellectual satisfaction. Reality may transcend not just what we currently know, but what we can know, what we can formulate, what we can conceptualize. This possibility generates a certain cosmic humility, a recognition that our knowledge, vast as it has become, remains bounded by horizons both observational and theoretical. The silent border of the cosmos reminds us of these limits, of the edge where certainty fades into probability, where observation gives way to inference, where knowing transitions to wondering. It marks not just the boundary of the observable universe, but the frontier of human understanding. Yet this same recognition inspires a profound wonder, an appreciation for how much we have discovered despite these constraints, for how far human knowledge has progressed in understanding a cosmos not designed for our comprehension. From our tiny planet orbiting an ordinary star in an ordinary galaxy, we have discerned the age and scale of the universe, traced its evolution from a hot, dense beginning to its current state, predicted and confirmed the existence of phenomena from black holes to gravitational waves to the cosmic microwave background. This remarkable progress suggests that while knowledge has horizons, these horizons continually expand. What was once unknowable becomes known. What was once unimaginable becomes commonplace. What was once beyond the edge of understanding becomes incorporated into our cosmic vision. The silent border recedes as our instruments, our theories, our methodologies advance, revealing new territories for exploration, new mysteries for investigation. But as our circle of knowledge expands, so too does the circumference of mystery that surrounds it. Each discovery reveals new questions. Each answer generates new puzzles. Each advance in understanding opens new frontiers of ignorance. The cosmos remains inexhaustible, its mysteries unending, its depths unfathomable, even as our knowledge of it grows. The silent border shifts, but never disappears, a horizon that recedes as we approach, but cannot be eliminated. This dynamic between knowledge and mystery, understanding and wonder, shapes our relationship with the cosmos. We are not passive observers, but active participants in an ongoing dialogue with reality, continually refining our theories, improving our observations, expanding our conceptual frameworks. The edge of what we can know is not a static boundary, but a shifting frontier, a challenge that inspires further exploration, further questioning, further discovery. At this frontier, we face questions that push the boundaries of scientific inquiry. What happened before the Big Bang? Did time itself begin, or did our universe emerge from some prior state? Is the multiverse real? And if so, what principles govern its structure? What is the ultimate fate of the cosmos, the final destination of its accelerating expansion? Does information survive inside black holes? And if so, how does it escape or become encoded on the horizon? These questions address domains beyond direct observation, epochs before our cosmic horizon, scales below our measurement capabilities, phenomena hidden behind event horizons. They challenge not just what we know, but how we know. What counts as evidence? What qualifies as a scientific explanation? They push us to refine our methodologies, to develop new theoretical frameworks, to find innovative ways of connecting the observable with the unobservable. In this pursuit, we employ not just observation and experiment, but mathematics and logic, theoretical modeling and computer simulation, thought experiments, and philosophical analysis. We extend our cognitive reach through these tools, transcending the limitations of our evolved intuitions, developing frameworks that allow us to conceptualize domains beyond direct sensory experience. Yet even these extended capabilities encounter limits. Gödel's incompleteness theorems show that any consistent formal system powerful enough to describe arithmetic contains truths that cannot be proven within that system. The halting problem in computer science demonstrates that there are computational tasks whose completion cannot be determined by any algorithm. The measurement problem in quantum mechanics reveals fundamental limits to what can be simultaneously known about certain pairs of properties. These limits are not merely practical but principled, not just constraints on what we currently know, but on what we can know, given the nature of knowledge itself. They define the edge where science meets philosophy, where empirical investigation transitions to theoretical speculation, where the answerable gives way to the perhaps unanswerable. This edge is not a failure of science, but a feature of reality, a consequence of the universe's structure and our place within it. The cosmos does not organize itself around our cognitive capabilities or observational technologies. It exists independent of our understanding, following principles that may transcend our ability to fully comprehend or articulate. The recognition of these limits need not diminish our scientific aspirations, but can inform them, guiding our efforts toward questions that, while challenging, remain tractable through empirical investigation and theoretical modeling. It encourages a balance between ambitious exploration and methodological restraint, between pushing the boundaries of knowledge and acknowledging where those boundaries become, at least temporarily, impassable. This balance seems particularly important at the silent border of the cosmos, where observation reaches its limits and theory must extend beyond direct empirical verification. Here, we navigate between the known and the unknown, the observable and the unobservable, the scientifically addressable and the perhaps permanently mysterious. We employ our most sophisticated tools, from mathematics to computer simulation to philosophical analysis, to peer beyond the edge of what we can directly see. Yet even with these tools, certain aspects of reality may remain permanently beyond our cognitive reach, hidden by horizons both observational and theoretical. The universe before the Big Bang, the reality beyond our cosmic event horizon, the interior of black holes, the ultimate nature of consciousness. These domains push at the boundaries not just of what we know, but of what we can know, what we can formulate, what we can conceptualize. This possibility generates not despair, but humility, not disappointment, but wonder. It reminds us that the cosmos is not exhausted by our theories, that reality exceeds our models, that the universe contains depths that our conceptual frameworks may never fully plumb. It places our knowledge in cosmic context, as remarkable but finite, expansive but bounded, growing but never complete. The edge of what we can know is not just where the universe becomes unobservable, but where our understanding reaches its limits, where our theories encounter their boundaries, where our concepts find their frontiers. It is the silent border not just of the cosmos, but of human comprehension, the threshold where the known meets the perhaps unknowable, where science meets mystery, where understanding transitions to wonder. Physics has limits: observation, theory, prediction. Perhaps the silence is not just out there. Perhaps it is also within. Time flows differently across the cosmos. This simple truth, revealed by Einstein's theories of relativity, transforms our understanding of the silent border. The edge we seek is not merely spatial but temporal, not just a place but a moment. Not only a boundary in the three dimensions we directly perceive, but a frontier in the fourth dimension that weaves through them all. Time, that most familiar yet elusive dimension, does not tick at a constant rate throughout the universe. It stretches and compresses, speeds up and slows down, depending on gravity and motion. Near massive objects like black holes, time dilates, flowing more slowly than in the emptier regions of space. For objects moving at high velocities relative to an observer, time also slows, an effect that becomes profound as speeds approach that of light. This relativistic nature of time creates a temporal aspect to the cosmic border. The edge is not just where space ends or observation fails, but where time itself behaves differently, where the familiar flow of seconds, minutes, years breaks down, or transforms into something almost unrecognizable. The silent border has a temporal dimension that shapes our understanding of what lies beyond. Consider a clock near the event horizon of a black hole. From the perspective of a distant observer, this clock appears to tick more and more slowly as it approaches the horizon, eventually freezing completely at the boundary itself. Time, from the external viewpoint, stops at the event horizon. Yet from the perspective of an observer falling with the clock, time continues to flow normally, and the horizon is crossed without any local disruption in the temporal sequence of events. This dramatic divergence between perspectives reveals a fundamental aspect of cosmic boundaries. They are often relative rather than absolute, dependent on the observer's position and motion, existing in the relationship between viewpoints, rather than as objective features of reality. What constitutes a border for one observer may not be a border for another. The edge, in this sense, is perspectival, a function of how we observe and measure rather than an intrinsic property of the cosmos itself. This relativistic understanding of time also affects our perception of distant events. When we observe galaxies billions of light years away, we see them not as they are now, but as they were billions of years ago, when the universe was much younger. The light from these ancient epochs has spent billions of years crossing the expanding cosmos to reach our telescopes, carrying images of a universe radically different from its current state. This temporal disconnect means that the universe we observe does not exist simultaneously. Different regions appear to us at different cosmic ages, creating a kind of temporal map, with the youngest regions at the center, nearest to Earth, and progressively older ones toward the edge of our observable bubble. The silent border, in this sense, marks not just the edge of observable space, but the limit of observable time, the earliest moments of cosmic history visible to our instruments. At this temporal boundary lies the cosmic microwave background, the afterglow of the Big Bang itself, radiation released when the universe was just 380,000 years old. This faint glow, detectable in all directions, marks the limit of electromagnetic observation, the point beyond which the universe was opaque to light. It represents a time horizon, a moment before which we cannot directly observe with conventional telescopes. But cosmic time extends beyond this visual border. The universe existed before it became transparent, evolving through earlier phases that left indirect traces we can study. The abundances of light elements like hydrogen, helium, and lithium reflect conditions during the first few minutes after the Big Bang, when nuclear fusion in the hot, dense primordial plasma created the building blocks of all later cosmic structures. These abundances provide a window into an epoch before the cosmic microwave background, a glimpse beyond the time horizon of direct observation. Other messengers can carry information from even earlier moments. Neutrinos, those ghostly particles that rarely interact with matter, decoupled from the primordial plasma when the universe was just 1 second old. Detecting these primordial neutrinos would open a window onto a much earlier phase of cosmic evolution, though their extremely low energy makes such detection extraordinarily challenging with current technology. Gravitational waves offer another potential window into the early universe. These ripples in space-time, caused by violent cosmic events, propagate freely through matter without scattering or absorption. Future gravitational wave observatories might detect echoes from cosmic inflation, the exponential expansion thought to have occurred within the first fraction of a second after the Big Bang, providing our earliest direct observational window onto cosmic history. But even these alternative messengers cannot penetrate to the very beginning. The Planck epoch, the first 10 to the negative 43 seconds, remains hidden behind a veil of quantum gravity, a domain where our current theories break down completely. Here, the fundamental forces unify, space-time becomes granular, and quantum fluctuations dominate, creating conditions so extreme that general relativity and quantum field theory, our best descriptions of gravity and particle physics, cannot jointly describe them. This earliest moment represents a temporal border more profound than any spatial boundary. It marks not just a limit to what we can see, but a threshold beyond which our understanding of physical law itself becomes uncertain. Before the Planck time, space and time as we understand them may not have existed in recognizable form. The concept of before itself becomes problematic, as time may have emerged from a more fundamental reality rather than extending infinitely into the past. Some cosmological models suggest that time, as we experience it, had a beginning, emerging along with space in the Big Bang. Others propose cyclic scenarios, where our universe represents just one phase in an eternal cycle of expansion and contraction, big bangs and big crunches. Still others envision a quantum tunneling from nothing, a spontaneous emergence of space-time from a state without conventional temporal progression. These models challenge our intuitive understanding of time as an infinitely extended dimension, flowing uniformly from past to future. They suggest that time itself may have borders, beginnings, or transitions, moments where its nature fundamentally changes. The silent border of the cosmos, in this perspective, includes not just the edge of observable space, but the limits of time itself, the moments where temporal concepts reach their frontier. This temporal aspect of the cosmic border becomes even more pronounced when we consider the future. Cosmic expansion, currently accelerating due to the influence of dark energy, shapes not just what we can see now, but what we will ever be able to see. Galaxies beyond our event horizon, approximately 16 billion light-years in the current era, recede faster than light due to cosmic expansion. Their signals, even traveling at light speed, can never reach us, creating a temporal border in the future, a limit to what events can ever affect our cosmic neighborhood. This future horizon contracts as dark energy drives accelerating expansion. Galaxies that are visible today will, in the distant future, accelerate beyond our horizon, their light unable to reach future observers on Earth. The observable universe shrinks over cosmic time, encompassing an ever smaller fraction of what exists. The temporal border draws closer, a shrinking bubble of visibility in an expanding cosmos. In the far future, trillions of years from now, only galaxies bound to our local group will remain visible. All other galaxies will have accelerated beyond our horizon, their light unable to counteract cosmic expansion. The universe will appear to future observers as a small island of galaxies in an otherwise empty void, a tiny oasis of visibility in an invisible cosmos. Time will have sealed off most of the universe from observation, creating a temporal bubble beyond which nothing can be seen. As cosmic expansion continues, even the fabric of time itself thins and stretches. The universe cools, its energy dispersing across ever-increasing volume. Structure formation ceases, with gravity no longer able to counter the relentless pull of dark energy. Stars burn out, matter decays, black holes evaporate through Hawking radiation. The cosmos approaches a state of near-perfect emptiness, a void in which events become increasingly rare, separated by vast gulfs of temporal nothingness. In this distant future, time loses its meaning as a measure of change. With few events to mark its passage, with matter so diffuse that interactions become vanishingly rare, time stretches toward a kind of eternity, a near stasis in which nothing happens for unimaginable spans. The cosmic time border approaches a limit state, a future in which temporal concepts themselves become almost meaningless in a universe frozen in perpetual expansion. This eventual heat death, this temporal twilight of the cosmos, represents another aspect of the silent border. Not a place where observation ends, but a time when the observable approaches zero, when the universe becomes so diffuse, so cold, so close to perfect entropy that nothing meaningful can occur. Time continues in principle, but with so little happening, it becomes an empty dimension, a parameter without significance. Between the temporal borders of the earliest moments and the latest epochs stretches the habitable era of the cosmos. The time when stars shine, planets form, complexity emerges. We live in this middle period, when the universe has cooled enough from its initial fireball to allow atoms and molecules, but remains hot enough to power nuclear fusion in stellar cores. This era is neither the beginning nor the end, but the cosmic spring and summer, the time of growth and flourishing. Yet even within this habitable era, time flows unevenly across the cosmos. Near black holes, neutron stars, and other massive objects, gravitational time dilation creates pockets of slower temporal flow. For a clock orbiting close to a black hole, decades might pass in regions far from strong gravity, while only seconds elapse near the event horizon. These temporal distortions create a kind of geographic distribution of time rates, a cosmic landscape where the fourth dimension varies from place to place. This uneven flow of time affects the evolution of the universe itself. Regions of higher density, where gravity is stronger, evolve more slowly in cosmic terms than less dense regions. Galaxies at the centers of massive clusters age differently than those in cosmic voids. The universe develops not just spatially but temporally, with different regions evolving at different rates depending on their gravitational environment. This differential aging combines with the finite speed of light to create a cosmic perspective unlike anything in everyday experience. When we observe distant galaxies, we see them not only as they were in the past, but as they were in a universe with different properties, different densities, different rates of expansion. The images we receive come not just from earlier times, but from a cosmos in a different phase of its evolution, operating under conditions that no longer exist locally. Time's relativity also affects the future of the cosmos. As expansion accelerates, galaxies achieve an apparent speed away from us that increases with distance. Those sufficiently far move away faster than light, not because they break the cosmic speed limit, but because space itself expands rapidly enough to carry them beyond it. This superluminal recession creates the event horizon, a boundary beyond which events can never affect us, no matter how long we wait. This future aspect of the cosmic border represents a kind of temporal segregation, a division of the universe into causally disconnected regions. What happens beyond our event horizon cannot influence our future, cannot send signals that will ever reach us, cannot participate in our cosmic evolution. These regions exist, presumably with their own galaxies and perhaps life. But from our perspective, they might as well not exist. They lie beyond our temporal reach, separated not by distance alone, but by the relativistic structure of space-time itself. The combination of past and future temporal borders creates a kind of cosmic diamond, a four-dimensional region centered on any observer, containing all events that could potentially be influenced by, or influence that observer. Within this diamond, causal connection is possible. Beyond it lies territory invisible in principle, unknowable through direct observation, accessible only through theoretical extrapolation. This diamond represents the true silent border, the edge not just of what we can see, but of what can affect us or be affected by us throughout cosmic history. This causal diamond shrinks as dark energy drives accelerating expansion. Its future portion contracts as galaxies accelerate beyond our horizon, limiting what we can eventually observe. The cosmic end state, for observers in any given galaxy, becomes increasingly isolated, a temporal island surrounded by regions causally disconnected, a bubble of visibility in an otherwise invisible universe. Time seals off more and more of the cosmos from causal contact, creating a border that constricts with each passing eon. The silent border of the cosmos thus has a temporal dimension that fundamentally shapes our understanding of what lies beyond. It marks not just where space becomes invisible, but when events become unobservable, either because they occur before our earliest detection capabilities, or after light from them can no longer reach us. The border exists in time as well as space, a four-dimensional boundary enclosing the cosmic diamond of causal connection. This temporal aspect of the border challenges our conventional notions of beyond. What exists beyond the temporal limits of observation? Does time itself have an edge, a beginning or an end? Did it emerge from something timeless? Or has it always existed in some form? Will it eventually cease to have meaning in a universe approaching perfect entropy? Or will new structures, new dynamics, new forms of complexity emerge in the distant future? These questions push at the boundaries of physical theory, of philosophical understanding, of human comprehension itself. They remind us that the cosmos is not just vast in space, but deep in time, extending backward toward origins we struggle to reconstruct, and forward toward fates we can only dimly foresee. The silent border encompasses not just the edge of visible space, but the limits of accessible time, the threshold where temporal concepts themselves approach their frontier. Consider the earliest moment we can currently describe, the Planck time, 10 to the negative 43 seconds after what we conventionally call the beginning. Before this moment, quantum effects dominate gravitational ones, creating conditions where space and time themselves may not exist in recognizable form. Some theories suggest that time emerges from a more fundamental, timeless reality, that temporal progression itself is not primitive, but derived, not basic, but emergent. This perspective transforms our understanding of the temporal border. It becomes not just a limit to what we can observe, but a transition to a radically different type of reality, one without before and after, without duration or sequence, without the temporal flow that defines our experience of existence. The border marks not just a beginning of time, but a boundary between the temporal and the timeless, the sequential and the simultaneous, the evolving and the eternal. Similarly, the distant future approaches a state where time loses practical significance. As matter disperses, as interactions become increasingly rare, as events thin out across unimaginable spans, temporal measurement approaches meaninglessness. With nothing to mark its passage, with change occurring at intervals approaching infinity, time becomes an empty parameter, a dimension without structure, a coordinate without events to locate within it. This future temporal border represents not the end of time in a formal sense, but its fading into irrelevance, its transformation from a dimension packed with events to one so empty, so structureless, so devoid of change that it ceases to function as a meaningful aspect of reality. Time does not stop, but slows to an effective standstill, a near stasis in which eons pass between events of any significance. Between these temporal borders, past and future, stretches the era of complexity, the time when matter organizes into structures, when stars form and burn, when life can potentially emerge and evolve. We occupy a privileged moment within this span, when the universe has cooled enough to allow atoms, molecules, and life, but remains hot enough to power stars and active galactic nuclei. Our time is neither the beginning nor the end, but the middle, the cosmic equivalent of spring and summer in a universe evolving from fiery birth toward frozen silence. Yet even this habitable era does not last forever. Star formation peaked approximately 10 billion years ago and has been declining ever since. In about 1 to 10 trillion years, depending on their mass, the last stars will exhaust their nuclear fuel and fade to darkness. Galaxies will dim as their stellar populations age and die, becoming invisible collections of stellar remnants, cold planets, and diffuse gas, detectable only through their gravitational influence on surrounding matter. As stars die and matter disperses, the rate of significant cosmic events slows dramatically. Events that now occur frequently like supernovae, stellar collisions, and gamma-ray bursts, become increasingly rare, separated by vast gulfs of temporal emptiness. The cosmic event rate decreases exponentially, with intervals between noteworthy occurrences growing from millions to billions to trillions of years. Time stretches like a thinning fabric, expanding between events until its texture becomes almost imperceptible. In this way, time's role in the cosmic border becomes clear. It is not just a coordinate along which the universe evolves, but a dimension with its own structure, its own limits, its own borders. It begins in a state where temporal concepts break down in the quantum foam of the earliest instance. It flows unevenly across the cosmos, speeding up and slowing down depending on gravity and motion. It thins and stretches in the distant future, approaching a kind of emptiness where change becomes vanishingly rare. The silent border is not only where the universe falls quiet in space, but where it approaches silence in time as well, where events become so separated, so infrequent, so lacking in causal connection, that the cosmic narrative itself fades to a whisper. The border is temporal as well as spatial, a limit not just to where, but to when we can observe, know, comprehend the cosmos in all its complexity. The border is not only spatial, but temporal. Time slows near gravity, accelerates with expansion. In a far future universe, even time may stop flowing meaningfully. A silent border in time as well as space, where motion and heat fade into stillness. Our journey to the silent border of the cosmos draws to a close. We have traveled across vast distances and deep time, from the bright centers of galaxies to the dark voids between them, from the fiery birth of the universe to its cooling future. We have explored the limits of observation, the boundaries of knowledge, the edge where the visible fades into the invisible. This border we have sought is not a wall or a barrier, not a physical edge where space simply stops. It is a horizon of perception, a limit to what we can see from our particular vantage point in space and time. Beyond it, the universe continues, filled with galaxies and stars, planets, and perhaps life, all evolving and existing in regions forever hidden from our view. The silent border takes many forms. It appears as the particle horizon, the maximum distance from which light could have reached us since the beginning of time. It manifests as the event horizon, the boundary beyond which events can never affect us, no matter how long we wait. It emerges in the opacity of the early universe, the wall of plasma that blocks electromagnetic observation beyond the cosmic microwave background. It reveals itself in the quantum uncertainty at the smallest scales and the information paradox of black holes. Each of these horizons limits what we can observe, what we can know, what we can understand about the cosmos. Each defines a border between the visible and the invisible, the accessible and the inaccessible, the known and the perhaps unknowable. Together, they create the silent edge, the place where the universe falls quiet, not through absence of sound, but through absence of signal, through the inability of information to cross vast gulfs of space and time. This silence is not empty but full, not meaningless, but profound. It reminds us of our cosmic context, our place in a universe far larger than what we can observe, our moment in a history far deeper than what we can reconstruct. It humbles us with the vastness beyond our vision, with horizons that recede as we approach them, with questions that generate new mysteries even as we resolve old ones. Yet this same silence inspires wonder, curiosity, the persistent human drive to understand what lies beyond our immediate experience. It spurs us to develop new instruments, new theories, new ways of peering past apparent limits, of extracting information from faint signals, of inferring what exists from traces left within our observable bubble. The silent border challenges us to expand our cosmic vision, to push the boundaries of knowledge, even as we acknowledge their existence. In this quest, we employ not just telescopes and detectors, mathematics and modeling, but imagination and creativity, the uniquely human capacity to conceive what might exist beyond the edge of observation. We construct theoretical frameworks that extend beyond what we can see, guided by the patterns we observe within our horizon, constrained by logical consistency and explanatory power. We use these frameworks to peer beyond the silence, to envision what might exist in regions forever hidden from direct view. These speculations, these theoretical extrapolations, these imaginative extensions beyond the observable, are not mere flights of fancy, but disciplined explorations, guided by evidence, constrained by physical law, tested through their implications for phenomena we can detect. They represent science at its most ambitious, reaching beyond immediate observation, toward deeper understanding, toward more comprehensive frameworks, toward truth that transcends the limits of direct measurement. The silent border thus becomes not just a limit, but an invitation, not just an edge, but a frontier, not just a boundary, but a challenge to human ingenuity and understanding. It marks not the end of knowledge, but its leading edge, the place where certainty gives way to possibility, where observation transitions to inference, where knowing becomes wondering. As we stand at this frontier, gazing outward toward regions we cannot see, and inward toward questions we cannot fully resolve, we might feel a sense of cosmic loneliness, a recognition of our isolation in the vastness of space and time. We orbit an ordinary star in an ordinary galaxy, surrounded by billions of light years of mostly empty space, separated from other potential observers by gulfs so vast that communication seems almost impossible. The silence of the cosmos can seem profound, almost overwhelming in its immensity. Yet this same vastness, this same silence, connects us to the universe in ways both material and conceptual. The atoms in our bodies were forged in stellar furnaces, scattered by ancient supernovae, gathered into our solar system, and eventually, our planet. We are quite literally made of stardust, our physical existence, a direct consequence of cosmic evolution. The silence between stars is not a disconnection, but the medium through which light and matter and information flow, the space that both separates and connects all cosmic structures. Conceptually too, we connect to the cosmos through our capacity to understand it, to discern its patterns, to reconstruct its history, to predict its future evolution. Our minds, evolved on a small planet orbiting an ordinary star, nevertheless grasp the age and scale of the universe, the forces that shape it, the principles that govern its development from quantum fluctuations to large-scale structure. The silence does not prevent understanding, but invites it, challenging us to listen more carefully, to observe more precisely, to think more deeply about what we detect and what remains hidden. This connection, both material and conceptual, reminds us that we are not merely observers of the cosmic drama, but participants in it. Our observations, our theories, our understanding become part of the universe's story, part of how reality comes to know itself through conscious beings evolved within it. The silent border is not just something we perceive, but something we help define through our observations, our theories, our conceptual frameworks. As our journey concludes, let us remember that the silent border is not where the universe ends, but where our perception reaches its current limits. Beyond it, the cosmos continues, perhaps without end, filled with wonders we can only imagine, with realities that may transcend our conceptual frameworks, with mysteries that future observers might resolve, in ways we cannot yet conceive. The cosmos began with light, but it ends in silence. Not death, but stillness. Not nothing, but everything at rest. The border is not where things end. It's where we stop asking and begin listening. Sleep now, beneath a sky that stretches into silence. In this stillness, in this quiet contemplation of cosmic horizons, we find not despair but peace, not disappointment but acceptance, not an end but a transition. The silent border reminds us that the universe is not exhausted by our theories, that reality exceeds our models, that the cosmos contains depths our instruments may never plumb and heights our equations may never reach. It places our knowledge in context, as remarkable but finite, expansive but bounded, growing but never complete. Let us rest in this recognition, finding peace in the vastness we cannot fully comprehend, comfort in the mysteries that exceed our grasp, wonder in the silence that surrounds our island of understanding. Let us sleep beneath a canopy of stars that extends beyond our vision, dreaming perhaps of what lies beyond the edge, beyond the horizon, beyond the silent border of the cosmos. The cosmos began with light, but it ends in silence. Not death, but stillness. Not nothing, but everything at rest. The border is not where things end. It's where we stop asking and begin listening. Sleep now, beneath a sky that stretches into silence.